Welcome back to Sleep Space. Sit back, relax, and enjoy the show. What if the universe had a speed limit that nothing could ever break? A barrier woven into the fabric of space and time itself. But what if, just maybe, there were ways to bend the rules, beyond the cosmic speed limit? In the vast expanse of our universe, few concepts have captured human imagination quite like the speed of light. From science fiction tales of warp drives to late-night conversations about the cosmos, the question inevitably arises: is there anything faster than light? The conversation typically unfolds like a familiar dance. Someone claims to have heard about something exceeding light speed. Another person confidently counters that nothing can travel faster than light. Then comes the inevitable challenge. Oh yeah. What about? This chapter explores the fascinating reality behind this cosmic speed limit, examining both the rule and its apparent exceptions. The ultimate speed limit. Light travels at an astonishing 299,790,2458 meters per second in a vacuum. This speed is so fundamental to our understanding of physics that it's represented by the constant c in Einstein's famous equation, E equals mc2. To put this speed in perspective, light could circle Earth's equator about 7.5 times in just 1 second. A beam of light could travel from Earth to the Moon in just 1.3 seconds. This same beam would take about 8 minutes and 20 seconds to reach us from the Sun. When we gaze at our nearest stellar neighbor, Proxima Centauri, we're seeing it as it existed about 4.24 years ago. The light from distant galaxies has been traveling for millions or even billions of years before reaching our telescopes. Einstein's special theory of relativity, published in 1905, established that the speed of light in a vacuum is constant regardless of the observer's motion. This revolutionized our understanding of space and time. Prior to Einstein, physicists assumed that space and time were fixed, absolute frameworks within which everything else moved. Einstein showed that space and time are actually flexible, forming a four-dimensional fabric called spacetime. As objects approach the speed of light, strange effects begin to manifest. Time slows down, a phenomenon known as time dilation. Lengths contract in the direction of motion. Mass increases, requiring ever more energy to accelerate further. These effects aren't just theoretical, they're observed regularly in particle accelerators and cosmic rays. At the Large Hadron Collider, particles routinely travel at 99.999999% the speed of light, experiencing all these relativistic effects. The energy required to accelerate an object with mass to the speed of light would be infinite. This creates an insurmountable barrier that prevents anything with mass from reaching, let alone exceeding, light speed. Light in different mediums. While light speed in a vacuum is constant, light actually travels slower when passing through matter. In water, light travels at about 75% of its vacuum speed. In glass, it slows to roughly 67%. Even air slightly reduces light speed, though by less than 1%. This reduction in speed causes light to bend when passing between different materials, a phenomenon called refraction. This is why a straw appears bent in a glass of water, or why a swimming pool looks shallower than it actually is. When light enters a denser medium, it slows down because photons interact with the atoms in the material. They are absorbed and re-emitted, creating a slight delay in the light's journey. The photons themselves don't actually slow down. Rather, their path becomes more circuitous as they bounce between atoms. Interestingly, certain particles can exceed the speed of light in a particular medium, while still obeying the universal speed limit. For example, when high-energy charged particles move through water faster than light can travel through that same water, They produce a blue glow called Cherenkov radiation. This is similar to the sonic boom created when an object exceeds the speed of sound in air. Nuclear reactors often glow with this distinctive blue light, as charged particles from nuclear reactions exceed the speed of light in water. This phenomenon powers neutrino detectors like Super Kamiokande in Japan, which uses a massive tank of ultra-pure water to detect these elusive particles. However, these particles are still traveling slower than light would in a vacuum, preserving Einstein's cosmic speed limit. Common misconceptions about faster-than-light travel. Science fiction has popularized numerous concepts that seem to circumvent the light speed barrier. Star Trek's warp drive, Star Wars hyperspace, and countless other fictional technologies promise instant travel across vast interstellar distances. These stories have shaped public perception about what might be possible. A common misconception is that scientists have already achieved faster-than-light travel in laboratories. Headlines about quantum teleportation or entanglement often fuel this misunderstanding. However, these phenomena don't actually transmit information faster than light. Another misconception involves theoretical concepts like wormholes or the Alcubierre warp drive. While these mathematical solutions to Einstein's equations suggest potential loopholes, they require exotic matter with negative energy density or face other significant physical barriers. They remain firmly in the realm of theoretical physics, not practical engineering. Many people also misunderstand what scientists mean by the expanding universe. While distant galaxies appear to recede from us faster than light, they're not actually moving through space at those speeds. Rather, space itself is expanding, carrying these galaxies along with it. This distinction is crucial for understanding cosmic speed limits. Apparent exceptions. When things seem faster than light, several phenomena might appear to violate the light speed limit at first glance. Quantum entanglement, sometimes called spooky action at a distance, involves particles that share a quantum state regardless of their separation. When one particle is measured, the other instantaneously correlates its properties, seemingly communicating faster than light. However, this doesn't allow for faster-than-light communication because the outcome of each measurement is random and cannot be controlled to transmit information. The expansion of the universe presents another apparent exception. Galaxies more than about 14 billion light-years away are receding from us faster than light. This doesn't violate relativity because the galaxies aren't moving through space faster than light. Rather, the space between us is expanding. Imagine dots on a balloon's surface as the balloon inflates. The dots themselves aren't moving across the rubber, but they still grow farther apart. Phase velocity is another phenomenon that can exceed light speed without violating physical laws. This describes how fast the phase of a wave travels, rather than energy or information. For example, the shadow of your hand on a distant wall can move faster than light if you rotate your wrist quickly enough. No energy or information travels faster than light in this scenario. A similar effect occurs when a laser pointer sweeps across the surface of the moon. The spot of light can move across the lunar surface faster than light speed, but no actual photons are traveling faster than c. The consequences of light speed limit. The cosmic speed limit has profound implications for our dreams of space exploration. Even at light speed, the journey to Proxima Centauri would take over 4 years. Reaching the center of our Milky Way galaxy would require about 26,000 years. Intergalactic travel becomes virtually impossible within human lifespans. This limitation shapes our search for extraterrestrial intelligence as well. Radio signals from potentially habitable planets dozens or hundreds of light years away would take decades or centuries to reach us. Any conversation would unfold over generations, not minutes. The speed of light also affects our understanding of causality, the relationship between cause and effect. If information could travel faster than light, it would be possible in some reference frames to receive a message before it was sent, creating paradoxical situations. The light speed limit preserves the logical ordering of events throughout the universe. For astronomers, light's finite speed means that looking deep into space is also looking back in time. When we observe a galaxy 10 billion light-years away, we're seeing it as it existed 10 billion years ago. This gives us a remarkable window into cosmic history, allowing us to study the evolution of the universe directly. The historical journey, how we discovered light speed. Humanity's quest to measure the speed of light spans centuries of ingenious experiments. In the early 17th century, Galileo attempted to measure light speed by uncovering lanterns at measured distances. His assistants would uncover their lanterns when they saw his light, but the delay was imperceptible. Galileo could only conclude that light traveled at least 10 times faster than sound. The first successful measurement came from Danish astronomer Ole Romer in 1676. He noticed that the eclipses of Jupiter's moon Io appeared to occur earlier when Earth was moving toward Jupiter and later when Earth was moving away. Romer correctly attributed this to the finite speed of light and calculated it to be about 220,000 kilometers per second, remarkably close to the modern value considering his limited instruments. In 1849, Hippolyte Fizeau devised an elegant experiment using a rapidly rotating toothed wheel. Light passed through a gap in the wheel, traveled to a distant mirror, and returned through another gap if the wheel rotated at just the right speed. This allowed Fizeau to calculate light speed with improved accuracy. Albert Michelson refined these measurements in the late 19th century using rotating mirrors. His experiments, including the famous Michelson-Morley experiment, not only provided more precise measurements, but also helped disprove the existence of the luminiferous ether, a hypothetical medium once thought necessary for light propagation. Today, the speed of light is defined as exactly 299,792,458 meters per second. Rather than measuring the speed of light, we now use it to define the meter, fixing the value of c by international agreement in 1983. Thought experiments, visualizing light speed limitations. Imagine boarding a spaceship capable of continuous acceleration at 1g, the acceleration we feel on Earth's surface. This would create artificial gravity inside the ship identical to Earth's, making for a comfortable journey. After 1 year of such acceleration, you would reach about 77% of light speed. After 2 years, you'd reach 97% of light speed. Remarkably, you could cross our entire Milky Way galaxy in just 20 years of ship time due to relativistic time dilation, though more than 100,000 years would pass on Earth. Another thought experiment involves twins, one who stays on Earth and another who travels on a near-light-speed journey. When the traveling twin returns, they would be younger than their Earth-bound sibling. This twin paradox illustrates how time dilation becomes significant at relativistic speeds. If we could somehow observe an object approaching light speed, we would see strange visual distortions. The object would appear rotated due to the relativistic aberration of light. Colors would shift toward the blue end of the spectrum in the direction of motion, while appearing redder in the opposite direction. These thought experiments help us grasp the profound implications of living in a universe with a cosmic speed limit. As we continue our exploration of the cosmos, we must reckon with this fundamental constraint on our ambitions. Yet perhaps the most remarkable aspect of light speed is not that it limits us, but that it connects us to the most distant reaches of the observable universe, allowing us to study cosmic history and contemplate our place within it. Chapter 2. The Cosmic Stretch: How Our Universe Grows. Unveiling the Expanding Cosmos. Let the expansion of the universe go on well. The universe itself is expanding. Because of that, galaxies move away faster the further they are from us. This simple observation revolutionized our understanding of the cosmos. When we gaze into the night sky, we are looking not just at distant objects, but at the dynamic stretching of space itself. The stars and galaxies we observe are participants in a cosmic ballet of expansion that began with the Big Bang and continues to this day. This chapter explores the remarkable discovery that we live in an expanding universe, how we measure this expansion, and what it means for the ultimate fate of everything we know. The discovery of cosmic expansion. In the 1920s, astronomers believed our Milky Way galaxy constituted the entire universe. The prevailing view was that the universe was static and unchanging, just as Isaac Newton and generations of scientists had assumed. Edwin Hubble changed everything. Working at Mount Wilson Observatory with its powerful 100-inch telescope, Hubble made observations that would forever transform our cosmic perspective. He first proved that certain nebulae were actually distant galaxies far beyond our Milky Way, instantly expanding the size of the known universe. But his most profound discovery came when he combined his observations with earlier work by astronomer Vesto Slipher. Slipher had noted that the light from most galaxies was redshifted, meaning their spectral lines were moved toward the red end of the spectrum. This phenomenon, known as redshift, occurs when a light source moves away from an observer, similar to how the pitch of a train whistle drops as it moves away from you. Hubble realized something remarkable. The farther a galaxy was from Earth, the greater its redshift. This meant the farther galaxies were receding faster in a consistent relationship that became known as Hubble's law. This observation led to a stunning conclusion. The universe was not static but expanding in all directions. This discovery contradicted Einstein's own assumptions about a static universe, leading him to call his cosmological constant, which he had introduced to keep the universe static in his equations, his greatest blunder. The expansion of the universe represents one of the most profound paradigm shifts in the history of science. It fundamentally changed our understanding of cosmic origins and destiny. The fabric of spacetime. To truly understand cosmic expansion, we must first grasp what is actually expanding. It is not objects moving through space like shrapnel from an explosion. Rather, space itself is stretching. Imagine a loaf of raisin bread rising in the oven. As the dough expands, the raisins move apart from each other. From the perspective of any single raisin, all other raisins appear to be moving away. The farther a raisin is, the faster it appears to recede. Yet the raisins themselves are not moving through the dough. It is the expansion of the dough that carries them apart. Similarly, galaxies are not racing through static space. The very fabric of spacetime is stretching, carrying galaxies along with it. Another helpful visualization is a balloon with dots drawn on its surface. As you inflate the balloon, all dots move away from each other. From the perspective of any dot, all other dots appear to be moving away, with more distant dots receding faster. This balloon analogy helps illustrate another important concept. The expansion has no center. Just as there is no special dot at the center of the balloon's expansion, there is no central point from which the universe expands. Every point in the universe experiences expansion the same way. This leads to a profound realization. The Big Bang did not occur at a specific location in space. It happened everywhere at once, as the entire fabric of spacetime began to expand. Hubble's law and the cosmic speed limit. Hubble's law states that the recession velocity of a galaxy is proportional to its distance from us. Mathematically, this is expressed as v equals h0 times d, where v is the recession velocity, d is the distance, and h0 is the Hubble constant. The Hubble constant represents the current expansion rate of the universe. Determining its precise value has been one of astronomy's greatest challenges. Modern measurements using various techniques place the Hubble constant at approximately 70 kilometers per second per megaparsec. This means that for every megaparsec, about 3.26 million light-years of distance, galaxies recede about 70 kilometers per second faster. A galaxy 10 megaparsecs away recedes at about 700 kilometers per second. A galaxy 100 megaparsecs away recedes at about 7,000 kilometers per second. This relationship leads to a startling conclusion. At a certain distance, galaxies must be receding faster than the speed of light. This occurs at roughly 14 billion light-years in our current epoch. Does this violate Einstein's cosmic speed limit? Surprisingly, it does not. The universal speed limit applies to objects moving through space, not to the expansion of space itself. Galaxies are not moving through space faster than light. Rather, the space between them is expanding so rapidly that the total recession speed exceeds light speed. This creates a cosmic horizon beyond which we cannot observe. Light from galaxies beyond this horizon will never reach us, no matter how long we wait. Accelerating expansion and dark energy. For decades after Hubble's discovery, astronomers assumed the expansion of the universe must be slowing down due to gravity. The mutual gravitational attraction of all matter should gradually break the cosmic expansion. The key question seemed to be whether there was enough mass to eventually halt and reverse the expansion, leading to a big crunch, or if the universe would expand forever at an ever-decreasing rate. In the late 1990s, two independent teams of astronomers set out to measure this deceleration. Using Type Ia supernovae as standard candles, these distant cosmic explosions of consistent brightness allowed precise distance measurements. The results shocked the scientific community. The universe was not slowing down at all. It was accelerating. The expansion of the universe is speeding up, not slowing down. This discovery, which earned the 2011 Nobel Prize in Physics, demanded an explanation. What force could possibly counteract gravity on a cosmic scale? Scientists named this mysterious repulsive force dark energy. Dark energy appears to permeate all of space, creating a kind of negative pressure that drives galaxies apart at an accelerating rate. The nature of dark energy remains one of the greatest unsolved mysteries in physics. Current measurements suggest dark energy constitutes about 68% of the total energy content of the universe. Matter, both visible and dark, makes up the remaining 32%. This means the ultimate fate of our universe is largely determined by a force we barely understand. Cosmic horizons and the observable universe. The expansion of space creates fundamental limits to what we can observe. The observable universe is the spherical region around us from which light has had time to reach Earth since the beginning of the universe. Currently, this region extends about 46.5 billion light-years in all directions. This radius is much larger than the 13.8 billion years age of the universe, because space itself has been expanding as light travels through it. Beyond the observable universe lies the unobservable universe. We can never receive information from these distant regions, because the light from them will never reach us due to cosmic expansion. This creates a cosmic horizon, similar to the horizon at sea. Just as we cannot see ships beyond the Earth's curvature, we cannot observe galaxies beyond our cosmic horizon. This horizon is not fixed. As time passes, we can see farther in some directions as light from more distant regions finally reaches us. However, due to accelerating expansion, some galaxies currently within our observable universe will eventually disappear from view as they cross our cosmic horizon. Their light will be stretched to infinitely long wavelengths, effectively removing them from our observable universe forever. The fate of the universe. The discovery of accelerating expansion has profound implications for the ultimate fate of our universe. Before this discovery, cosmologists considered three possible scenarios. In a closed universe with sufficient mass, gravity would eventually halt expansion and pull everything back together in a big crunch. In a flat universe with exactly the critical density, expansion would continue forever but gradually slow to a near stop. In an open universe with insufficient mass, expansion would continue forever at a significant rate. The discovery of dark energy added a fourth, now most likely scenario. In this dark energy-dominated universe, expansion accelerates eternally. Over trillions of years, this accelerating expansion will pull apart galaxy clusters, then individual galaxies, then solar systems, and eventually even atoms themselves. This scenario, sometimes called the Big Freeze or Big Rip depending on specific dark energy models, paints a lonely future. In the far distant future, any observers would find themselves in an apparently empty universe, with all other galaxies having receded beyond the cosmic horizon. The night sky would be nearly empty, with only the remnants of their local group of galaxies visible. Measuring cosmic expansion, tools and techniques. Astronomers employ several methods to measure the expansion rate of the universe. Type Ia supernovae serve as standard candles because they consistently reach the same peak brightness. By measuring their apparent brightness and redshift, astronomers can determine both their distance and recession velocity. The cosmic microwave background, the afterglow of the Big Bang, contains tiny temperature fluctuations that provide information about the universe's geometry and expansion history. Baryon acoustic oscillations, the imprint of sound waves in the early universe, serve as a standard ruler that can be measured at different cosmic epochs. Gravitational waves from merging neutron stars, first detected in 2017, offer a new independent method to measure cosmic expansion. Interestingly, different measurement techniques currently yield slightly different values for the Hubble constant. This tension between measurements is one of cosmology's most intriguing puzzles and may point to new physics beyond our current understanding. As we continue to refine our measurements and develop new techniques, we hope to resolve these discrepancies and gain deeper insight into the nature of cosmic expansion. The expanding universe represents one of humanity's greatest discoveries. From a static, eternal cosmos centered on our galaxy, we now understand we live in a dynamic, evolving universe with a beginning and an ongoing expansion that shapes its destiny. This cosmic perspective humbles us, yet also inspires wonder at how our minds can comprehend such vast scales of space and time. In the next chapter, we will explore another fundamental aspect of our universe, the mysterious dark matter that outweighs all visible matter and shapes the cosmic web of galaxies we observe today. Chapter 3. The Cosmic Dance of Recession, How Galaxies Reveal Universal Expansion. The night sky appears static to our naked eyes, stars seemingly fixed in their celestial positions. Yet beneath this illusion of permanence lies one of astronomy's most profound discoveries. The universe is in constant motion, expanding in all directions like the surface of an inflating balloon. This revelation fundamentally transformed our cosmic perspective. When we peer through powerful telescopes at distant galaxies, we're not just looking across space, but back in time. The light from these cosmic islands has traveled for millions, even billions of years to reach our telescopes. This celestial light show reveals an astonishing pattern. The farther away galaxies are from us, the faster they appear to be moving away. This relationship between distance and recession forms the cornerstone of modern cosmology, the discovery that changed everything. In the 1920s, astronomer Edwin Hubble made an observation that would forever change our understanding of the cosmos. Using the 100-inch Hooker telescope at Mount Wilson Observatory, Hubble carefully measured the distances to numerous galaxies. He combined these measurements with earlier work by Vesto Slipher, who had documented the redshift in galactic spectra. What emerged was a clear pattern. Galaxies were receding from Earth at speeds proportional to their distance. This relationship, now known as Hubble's law, provides compelling evidence that we live in an expanding universe. The implications were revolutionary. If galaxies are moving apart today, then they must have been closer together in the past. Rewinding this cosmic film all the way back suggests that the entire universe once existed in an incredibly hot, dense state. This realization gave birth to the Big Bang theory, fundamentally reshaping our understanding of cosmic origins. The beauty of Hubble's discovery lies in its simplicity. The mathematical relationship can be expressed as V equals h0 times d, where v represents recessional velocity, d is distance, and h0 is the Hubble constant. This elegant equation describes the fundamental heartbeat of our expanding
inhabit
cosmos.
a little blue planet
Understanding
called Earth.
recessional
Earth
velocity.
is habitable
When
because it had the
astronomers
right
speak of
conditions
galaxies
and ingredients
receding,
to enable
they're
life as we
describing a
know it to
phenomenon
evolve
revealed
and
through
flourish.
spectroscopy.
And one of the most
Light from
important
distant
factors
galaxies
in making
shows a
our blue
systematic
planet
shift
habitable
toward
is
longer,
the wet stuff
redder
itself,
wavelengths.
water.
This
It's kind
cosmic
of
redshift is
extremely
analogous to
important
the
for life.
Doppler effect we
When it comes to the
experience
search
with
for
sound
habitable
waves when an
exoplanets,
ambulance
planets
passes
outside
by.
our solar
Its siren
system,
dropping
we
in
think the
pitch
ability
as
to
it
have
moves away
liquid
from
water on a
us.
planet's
The
surface
greater
is
the
just as
redshift,
important for
the
those
faster
worlds.
the galaxy
There's
is
a handy
moving away from
concept
Earth.
astronomers use
This
to help them
recessional
figure out where
velocity
to look
becomes a
around any
cosmic
given
speedometer,
star for
telling us
exoplanets
how
that
quickly
just
space
might have the
itself
right
is stretching
stuff for
between
life.
cosmic
It's
objects.
called the habitable
Importantly,
zone.
this
It's the
recession
distance
isn't
from a
about
star
galaxies
where a
moving through
rocky
space
planet
like
with an
cars on a
atmosphere could have
highway.
liquid water
Rather,
on its
space
surface.
itself is
In our
expanding,
solar system,
carrying
the habitable
galaxies
zone
along with
extends
it.
from around
The
the
fabric
orbit
of spacetime
Venus
stretches,
to around the orbit
increasing
of
the
Mars.
distance between
Earth happens
galaxies
to be
that aren't
nice
bound
and comfy
together by
in the
gravity.
middle. But it
An
takes
everyday
more than just a
analogy
good
helps
location.
clarify this
Orbiting
concept.
in the habitable
Imagine
zone
dots
does not
drawn on the
guarantee a
surface of a
planet will be
balloon.
habitable.
As you
After all,
inflate the balloon,
moon is
the dots
right
move
here
apart,
with us,
not
but
because
it's
they're
certainly
moving
not
across
habitable.
the surface,
Sorry, moon.
but because the
The
surface
location of
itself
the habitable
is
zone
expanding.
depends on how big
Similarly,
and bright a star
galaxies
is.
appear
The
to
nearest
recede
star to our
because
sun,
the
Proxima
cosmic
Centauri,
fabric
has
connecting
at
them
least one
stretches.
planet in the habitable
Modern
zone.
measurements of
But
recessional
because Proxima is
velocities
much smaller
require
and dimmer
sophisticated
than our sun,
spectroscopic
its habitable
equipment.
zone is way
Astronomers
smaller
identify
and closer
specific
to the
spectral
star.
lines from
So
elements like
every
hydrogen
star
and
has a
helium.
habitable zone.
Then
but
measure
that
how
doesn't
far
mean
these
there will
lines
be
have
planets
shifted
there.
from their laboratory
For example,
wavelengths.
the star known as Kepler
These
90
precise
is similar
measurements
to our
allow
sun,
us to
and it
calculate
too
exactly
has
how
8
fast
planets.
galaxies
But
are
they're
moving
all
away
huddled
from us.
super close to
Some
the star,
distant
well
galaxies
inside of the habitable
recede
zone.
at speeds
But the
approaching the
longer
speed of
we
light.
look, the more
Their
likely it
tremendous
becomes that
velocities,
one day
a
we'll find
testament
another
to the
little
vast
blue,
distances
water-covered
that
planet
separate
right
them
in
from
its
our Milky
own
Way.
comfy habitable
Measuring
zone.
cosmic
And
distances
that would be a planet
to establish
with a
the
closer look
relationship
indeed.
between distance and recession. Astronomers needed reliable methods to measure how far away galaxies truly are. This challenge spawned the cosmic distance ladder, a series of interlocking techniques that allow us to measure progressively greater distances. The first rung of this ladder uses parallax, measuring the apparent shift in a star's position as Earth orbits the Sun. This technique works well for stars within a few hundred light years, but becomes impractical for more distant objects. For greater distances, astronomers rely on standard candles, objects with known intrinsic brightness. By comparing how bright these objects appear from Earth with their actual luminosity, astronomers can calculate their distance. Cepheid variable stars were Hubble's preferred standard candles. These pulsating stars follow a precise relationship between their pulsation period and luminosity. By timing a Cepheid's pulsations, astronomers can determine its true brightness and therefore its distance. For the most distant galaxies, Type Ia supernovae serve as cosmic lighthouses. These stellar explosions occur when white dwarf stars reach a critical mass, resulting in remarkably consistent peak brightness. When astronomers spot these cosmic detonations in faraway galaxies, they can determine distances stretching billions of light years. The James Webb Space Telescope, launched in 2021, represents the newest frontier in distance measurement. Its infrared capabilities allow astronomers to peer through cosmic dust and observe objects at unprecedented distances, refining our understanding of the universe's expansion history. Galaxy clusters, cosmic metropolises, individual galaxies rarely exist in isolation. Most, including our Milky Way, belong to gravitationally bound groups called galaxy clusters. These cosmic metropolises contain hundreds or even thousands of galaxies, spanning millions of light years. The Virgo cluster, our nearest major galaxy cluster, contains about 1,500 galaxies and sits approximately 54 million light-years from Earth. The Coma cluster, a much larger collection, hosts thousands of galaxies about 321 million light-years away. Galaxy clusters play a crucial role in our understanding of cosmic expansion. While individual galaxies within clusters interact gravitationally, maintaining relatively stable configurations, the clusters themselves participate in the overall cosmic expansion. Measuring the recession of entire clusters provides cleaner data for calculating the Hubble constant. These massive structures also reveal the presence of dark matter. The visible galaxies in clusters move too quickly to be held together by the gravity of observable matter alone. This discrepancy provides compelling evidence for an invisible mass component that dominates the cluster's gravitational influence. The hot gas permeating galaxy clusters emits X-rays that astronomers can detect with space telescopes. The temperature and distribution of this gas offers additional clues about the cluster's mass and the influence of dark energy on cosmic structures. When we observe distant galaxy clusters, we're seeing them as they appeared millions or billions of years ago. This time machine effect allows astronomers to study how clusters have evolved throughout cosmic history, providing insights into the fundamental forces shaping our universe. The cosmic web, universe on the largest scales, step back far enough, and even galaxy clusters reveal themselves as mere nodes in a much grander structure. The cosmic web. This vast network consists of filaments, walls, and voids that stretch across billions of light years. Galaxy clusters tend to form at the intersections of filaments, where matter density reaches its peak. These filaments consist of dark matter scaffolding decorated with galaxies, like pearls on a cosmic string. Between these structures lie cosmic voids, enormous regions of relatively empty space spanning hundreds of millions of light years. The Sloan Digital Sky Survey has mapped portions of this cosmic web by measuring the positions of hundreds of thousands of galaxies. The resulting three-dimensional maps reveal stunning complexity, with structures reminiscent of neural networks or soap bubble formations. Computer simulations suggest this web-like structure emerged naturally from tiny density fluctuations in the early universe. Areas slightly denser than average attracted more matter through gravity, while less dense regions grew increasingly empty as matter flowed away from them. Over billions of years, this process amplified initial differences into the dramatic cosmic architecture we observe today. The cosmic web's expansion follows the same principles governing individual galaxies. Filaments stretch as space expands, increasing the distances between unbound structures while maintaining the integrity of gravitationally bound systems. This delicate balance between expansion and gravitational attraction shapes the evolution of cosmic structure across the largest scales we can observe. Dark energy, the cosmic accelerator. Perhaps the most surprising discovery about cosmic expansion came in the late 1990s. Two independent teams of astronomers, studying distant Type Ia supernovae, expected to find the universe's expansion slowing down due to gravity. Instead, they found the opposite. The expansion is accelerating. This unexpected finding earned the 2011 Nobel Prize in Physics and introduced a mysterious new component to our cosmic inventory: dark energy. Dark energy appears to be a property of space itself. As the universe expands, creating more space, the amount of dark energy increases proportionally, driving ever faster expansion. Current measurements suggest dark energy constitutes about 68% of the universe's total energy content, making it the dominant component of our cosmos. The nature of dark energy remains one of physics' greatest unsolved mysteries. It might represent Einstein's cosmological constant, a fundamental property of spacetime. Alternatively, it could be an exotic energy field or even a sign that our understanding of gravity requires revision at cosmic scales. Whatever its nature, dark energy is reshaping our cosmic destiny. If dark energy maintains its current properties, the universe will continue expanding at an accelerating rate. Eventually, galaxies beyond our local group will recede so rapidly that their light can never reach us, leaving future astronomers with an increasingly empty observable universe. Modern measurements and the Hubble tension. Nearly a century after Hubble's initial discovery, astronomers continue refining measurements of cosmic expansion. The current value of the Hubble constant is approximately 70 kilometers per second per megaparsec, meaning that, for every megaparsec, about 3.26 million light-years of distance, galaxies recede about 70 kilometers per second faster. However, a puzzling discrepancy has emerged in recent years. Measurements based on the cosmic microwave background, radiation left over from the early universe, yield a lower expansion rate than measurements based on nearby cosmic objects like Cepheid variables and supernovae. This discrepancy, known as the Hubble tension, suggests either systematic errors in our measurements or, more intriguingly, new physics beyond our current understanding. The James Webb Space Telescope is expected to provide crucial data to help resolve this tension. Its unprecedented sensitivity will allow more precise measurements of cosmic distances and expansion rates, potentially revealing whether we need to revise our cosmological models. As we continue to refine our measurements, we gain an increasingly detailed picture of cosmic expansion throughout the universe's history. This cosmic timeline helps us understand not just where the universe has been, but where it's going. The story of cosmic expansion reminds us that the universe is not static but dynamic, constantly evolving in ways that continue to surprise and challenge our understanding. The farther away galaxies are from us, the faster they recede, their light stretched to longer wavelengths as they participate in the grand cosmic expansion. This fundamental relationship, first glimpsed by Edwin Hubble, continues to guide our exploration of the universe's deepest mysteries. As we prepare to explore the enigmatic dark matter in the next chapter, we carry forward this essential insight. We inhabit a universe in motion, its expansion weaving the cosmic tapestry that connects all galaxies in a dance of recession and gravity. Chapter 4. The cosmic ballet, how the universe expands. Imagine standing on a vast, dark plain, watching countless lights slowly drifting away from you in all directions. The farther a light is, the faster it recedes. This isn't science fiction. It's the reality of our expanding universe, a cosmic ballet of unimaginable scale that continues to unfold around us every second. The discovery that changed everything. In the 1920s, astronomer Edwin Hubble made an observation that would forever change our understanding of the cosmos. While studying distant galaxies from Mount Wilson Observatory in California, he noticed something peculiar. The light from these galaxies was stretched toward the red end of the spectrum, indicating they were moving away from us. But the pattern wasn't random. Hubble realized that galaxies twice as far from Earth were moving away twice as fast. Those 3 times as distant were receding 3 times as quickly. This simple yet profound relationship became known as Hubble's law, the first empirical evidence that we live in an expanding universe. This discovery shattered the prevailing view of a static, unchanging cosmos that had dominated scientific thought for centuries. The universe, it turned out, was not a fixed stage but a dynamic, evolving entity. Hubble's discovery came as a shock to many, including Albert Einstein, who had previously added a cosmological constant to his equations of general relativity, specifically to prevent them from predicting an expanding universe. Einstein later called this his greatest blunder, as his original equations had correctly predicted cosmic expansion before observations confirmed it. The implications were staggering. If the universe is expanding, then rewinding the cosmic film suggests everything originated from a single point, a concept that would eventually lead to the Big Bang theory. Understanding Hubble's law. Hubble's law can be expressed by a simple equation. V equals h0 times d, where v is the recession velocity of a galaxy, d is its distance from Earth, and h0 is the Hubble constant. This constant represents the rate of cosmic expansion. Its current measured value is approximately 70 kilometers per second per megaparsec. To grasp what this means, consider that a megaparsec equals about 3.26 million light-years. For every megaparsec of distance between us and a galaxy, that galaxy moves away from us at about 70 kilometers per second faster. A galaxy 10 megaparsecs away recedes at roughly 700 kilometers per second, while one 100 megaparsecs distant flees at a blistering 7,000 kilometers per second. This relationship holds true in all directions, creating the illusion that we occupy a special place in the universe. However, observers in any galaxy would see the same pattern, all other galaxies appearing to move away from them. This reveals a profound truth. There is no center to the expansion. The universe isn't expanding into anything. Space itself is stretching everywhere. The raisin bread analogy. To visualize cosmic expansion, imagine a loaf of raisin bread dough rising in an oven. As the dough expands, every raisin moves away from every other raisin. Raisins that were initially closer remain closer, while those farther apart move away more quickly. From the perspective of any single raisin, all others appear to be moving away, with more distant ones receding faster. In this analogy, the raisins represent galaxies, while the expanding dough represents space itself. Just as no raisin sits at the center of the bread, no galaxy occupies the center of the universe. The expansion happens everywhere simultaneously. This also explains why clusters of galaxies that are twice as far are receding away from us twice as fast. It's not that galaxies themselves are moving through space like rockets. Rather, the space between them is stretching. This distinction is crucial for understanding the true nature of cosmic expansion. Measuring the Hubble constant. Determining the precise value of the Hubble constant remains one of astronomy's greatest challenges. When Hubble first calculated it in 1929, he estimated a value of about 500 kilometers per second per megaparsec, far higher than modern measurements. This discrepancy occurred because measuring vast cosmic distances is extraordinarily difficult. Today, astronomers use multiple methods to measure the Hubble constant. One approach relies on standard candles, astronomical objects with known intrinsic brightness. By comparing how bright these objects appear from Earth with how bright we know they actually are, astronomers can calculate their distance. Cepheid variable stars, which pulse with a regular rhythm directly related to their brightness, serve as excellent cosmic yardsticks for nearby galaxies. For more distant measurements, Type Ia supernovae, exploding white dwarf stars that always reach nearly the same peak brightness, allow astronomers to measure distances billions of light-years away. Another method uses the cosmic microwave background radiation, the afterglow of the Big Bang, to determine the expansion rate. Curiously, these different methods yield slightly different values for the Hubble constant. This discrepancy, known as the Hubble tension, represents one of cosmology's most intriguing puzzles and may hint at new physics beyond our current understanding. The redshift evidence. How do we know galaxies are moving away from us? The answer lies in a phenomenon called redshift. When a light source moves away from an observer, the wavelengths of its light stretch, shifting toward the red end of the spectrum. This is similar to how an ambulance siren drops in pitch as it passes by and moves away from you. By examining the light from distant galaxies, astronomers can identify specific spectral lines, bright or dark bands that appear at known wavelengths when certain elements absorb or emit light. In galaxies moving away from us, these lines appear at longer wavelengths than expected. The amount of this redshift directly indicates how fast the galaxy is receding. Edwin Hubble combined these redshift measurements with distance estimates to establish his famous law. For extremely distant galaxies, the redshift becomes so pronounced that visible light stretches into infrared wavelengths, requiring specialized telescopes to detect. The most distant known galaxies show redshifts indicating they're moving away at more than 90% the speed of light due to cosmic expansion. Expansion does not affect everything. An important misconception about cosmic expansion is that everything in the universe is growing larger. This isn't the case. Gravity and other forces bind objects like planets, stars, and even galaxies together, preventing them from expanding with space. Our solar system isn't getting bigger. Earth isn't expanding. Even the Milky Way galaxy maintains its size despite cosmic expansion. Only the vast intergalactic spaces grow larger over time. This explains why we don't notice expansion in our daily lives. The effect only becomes apparent at immense scales, where gravity's binding force is overcome by the stretching of spacetime. The Andromeda Galaxy, our nearest large galactic neighbor, is actually moving toward the Milky Way rather than away from it. This occurs because local gravitational attraction between our galaxies overcomes the expansion of space at our relatively close cosmic proximity. The accelerating universe. Perhaps the most shocking discovery in modern cosmology came in the late 1990s, when two independent research teams studied distant supernovae to measure cosmic expansion. They expected to find that the expansion was slowing down over time as gravity pulled galaxies back together. Instead, they found the opposite. The expansion is accelerating. Galaxies are moving away from each other faster now than they were billions of years ago. This unexpected finding earned the 2011 Nobel Prize in Physics and introduced a mysterious new component to our universe. Dark energy. Dark energy appears to be a property of space itself, creating a kind of anti-gravity that pushes galaxies apart. As the universe expands and creates more space, this repulsive force grows stronger, accelerating the expansion. Current measurements suggest dark energy constitutes about 68% of the universe's total energy content, making it the dominant component of our cosmos. Yet we understand almost nothing about its nature. The fate of the expanding universe. What does an expanding universe mean for our cosmic future? Before the discovery of accelerating expansion, cosmologists considered three possibilities. In a closed universe, gravity would eventually halt expansion, causing everything to collapse back in a big crunch. In an open universe, expansion would continue forever but gradually slow down. In a flat universe, expansion would continue at an ever-decreasing rate, approaching but never reaching zero. The discovery of accelerating expansion introduced a fourth, more unsettling possibility. If dark energy remains constant or strengthens, the expansion will continue accelerating forever. In the far future, galaxies beyond our local group will recede so rapidly that their light can never reach us. They'll fade from view, leaving future astronomers in a seemingly smaller, emptier universe. In the most extreme scenario, called the Big Rip, acceleration could become so intense that it tears apart galaxies, stars, planets, and ultimately atoms themselves. However, this outcome remains speculative and would occur, if at all, many billions of years in the future. Cosmic horizons and the observable universe. Cosmic expansion creates a fundamental limit to what we can observe. Light from sufficiently distant regions hasn't had time to reach us since the Big Bang, creating what's called our particle horizon, the boundary of our observable universe. Even more intriguing is the cosmic event horizon. Because of accelerating expansion, light emitted today from galaxies beyond a certain distance will never reach us, no matter how long we wait. These galaxies are forever beyond our observational reach. Our observable universe contains roughly 2 trillion galaxies, but the actual universe may be vastly larger or even infinite. We can only see a finite portion of it due to these horizons created by expansion and the finite age of the universe. The 70 kilometers per second per megaparsec expansion rate means that at a distance of about 4,300 megaparsecs, 14 billion light-years, galaxies appear to recede faster than light. This doesn't violate Einstein's theories because the galaxies aren't moving through space faster than light. Space itself is expanding between us. As we peer deeper into space, we look further back in time, eventually seeing the universe as it was shortly after the Big Bang. This allows astronomers to study cosmic evolution directly, watching the universe change across billions of years. The story of cosmic expansion reminds us of our dynamic place in an ever-changing universe. What began with Edwin Hubble's observations of distant galaxies has blossomed into a rich understanding of cosmic evolution, revealing a universe far more dynamic and mysterious than anyone imagined a century ago. As we continue to measure and refine our understanding of cosmic expansion, we edge closer to answering fundamental questions about the origin, evolution, and ultimate fate of everything that exists. In the next chapter, we'll explore another cosmic mystery, the invisible dark matter that seems to hold galaxies together despite the universe's relentless expansion. Chapter 5. Measuring the immeasurable, the mind-boggling scale of megaparsecs. The human mind struggles with large numbers. 10, 100, 1,000, these we can comprehend. A million becomes difficult, existing more as a concept than something we truly visualize. But a megaparsec, a distance equal to over 3 million light-years, stretches our comprehension to its breaking point. This chapter explores these incomprehensibly vast cosmic measuring sticks and what they reveal about our universe. The cosmic tape measure. What exactly is a megaparsec? To understand this cosmic unit, we must first grasp its smaller counterpart, the parsec. A parsec, short for parallax second, equals about 3.26 light years or roughly 19 trillion miles. The term originated from the method astronomers used to measure stellar distances through parallax, the apparent shift in a star's position, when viewed from different points in Earth's orbit. 1 megaparsec equals 1 million parsecs, or approximately 3.26 million light years. At this scale, we've transcended the distances between neighboring stars and entered the realm where entire galaxies become mere points of light. To put this in perspective, our Milky Way galaxy spans roughly 30 kiloparsecs, about 100,000 light years, in diameter. The nearest large galaxy to us, Andromeda, sits at a distance of only 0.78 megaparsecs. When astronomers discuss objects at distances of multiple megaparsecs, they're describing structures so remote that the light we see from them began its journey when dinosaurs still roamed the Earth. These measurements aren't just academic exercises. They form the foundation of our cosmic map, allowing scientists to chart the distribution of galaxies throughout the observable universe. Light years time capsules from the cosmos. A light year, the distance light travels in one Earth year, equals approximately 5.88 trillion miles. When we observe an object 1 light year away, we see it not as it exists now, but as it existed 1 year ago. This connection between distance and time creates a natural time machine through observation. The Andromeda galaxy, visible to the naked eye on dark nights, appears to us as it was 2.5 million years ago. The light we see tonight began its journey when our hominin ancestors were just learning to craft stone tools. When we observe galaxies at distances of several megaparsecs, we're peering billions of years into the past. The most distant galaxies visible to our most powerful telescopes exist at distances approaching 13 billion light years. We see them as they were when the universe was in its infancy, less than 1 billion years after the Big Bang. This cosmic look-back time provides astronomers with a unique opportunity to study galaxy formation and evolution directly. By observing galaxies at different distances, and therefore different points in cosmic history, scientists can piece together how these immense star systems form, grow, and change over billions of years. The universe itself serves as both laboratory and time capsule. Hubble's revolutionary discovery. In the 1920s, astronomer Edwin Hubble made an observation that would forever change our understanding of the cosmos. Using the 100-inch Hooker telescope at Mount Wilson Observatory, he measured the distances to several galaxies and compared them with their spectra. He noticed something remarkable. The farther away a galaxy, the more its light was shifted toward the red end of the spectrum. This redshift indicated that distant galaxies were moving away from us, and more surprisingly, the farther the galaxy, the faster it appeared to be receding. This relationship, now known as Hubble's law, led to one of the most profound discoveries in scientific history. The universe is expanding. The value that describes this relationship, how quickly galaxies move apart based on their distance, became known as the Hubble constant. Modern measurements place this value at approximately 70 kilometers per second per megaparsec. This means that for every megaparsec of distance between 2 points in space, the expansion of the universe increases their relative velocity by about 70 kilometers per second. At small scales within our galaxy, or even our local group of galaxies, gravity easily overcomes this expansion. But at distances of many megaparsecs, the cumulative effect becomes dominant. driving galaxies apart at speeds that can exceed the speed of light for sufficiently distant objects. This doesn't violate relativity because space itself is expanding, not the galaxies moving through space. The Hubble tension. In recent years, a scientific controversy has emerged around the precise value of the Hubble constant. Different measurement techniques yield slightly different values, creating what astronomers call the Hubble tension. Methods that rely on the cosmic microwave background, the afterglow of the Big Bang, suggest a value of about 67 kilometers per second per megaparsec. Techniques using more local measurements, such as observations of Cepheid variable stars and Type Ia supernovae, yield values closer to 73 kilometers per second per megaparsec. This discrepancy might seem small, but at cosmic scales, it creates significant differences in our models of the universe's evolution and ultimate fate. The tension might indicate new physics beyond our current understanding, perhaps involving dark energy or other exotic components of the cosmos. Resolving this tension remains one of the most active areas of cosmological research today. Cosmic humility. When we contemplate distances measured in megaparsecs, a profound sense of humility naturally follows. Our entire planet, with all its continents, oceans, mountains, and valleys, is less than a speck of dust on the cosmic scale. The Earth's diameter is roughly 12,700 kilometers. Light crosses this distance in just 42 milliseconds. By comparison, light requires 100,000 years to cross our galaxy and millions or billions of years to reach us from distant cosmic structures. This vast scale forces us to reconsider our place in the universe. Astronauts who have viewed Earth from space often report experiencing the overview effect, a cognitive shift in awareness from seeing our planet as a whole, suspended in the blackness of space. Now imagine an ultra-overview effect that comes from truly comprehending the megaparsec scale of the universe. From this perspective, not just nations but entire galaxies become united in their cosmic insignificance. Yet paradoxically, this very insignificance makes our existence all the more remarkable. In a universe so vast, we have managed to evolve consciousness capable of measuring and understanding these immense distances. Mapping the cosmic web. At scales of many megaparsecs, galaxies aren't randomly distributed throughout space. They form an intricate structure astronomers call the cosmic web. Galaxies cluster together in groups and clusters, which themselves form even larger structures called superclusters. Between these dense regions lie vast cosmic voids, enormous bubbles of nearly empty space, spanning tens or hundreds of megaparsecs. The largest known structure in the universe, the Hercules Corona Borealis Great Wall, spans an estimated 10 billion light-years, a distance so vast that light would take 10 billion years to cross it. This structure exists at the very limit of what we can observe with current technology. Modern astronomical surveys like the Sloan Digital Sky Survey have mapped millions of galaxies, revealing this web-like structure in unprecedented detail. These maps show that the distribution of matter in the universe resembles a sponge, with galaxies concentrated along filaments and sheets surrounding the cosmic voids. This structure isn't random, but reflects quantum fluctuations in the earliest moments after the Big Bang, amplified over billions of years by gravity. Beyond our cosmic horizon, despite our most powerful telescopes, we can only observe a finite portion of the universe, what astronomers call the observable universe. This region extends approximately 46.5 billion light-years in all directions, limited not by technology, but by the fundamental physics of an expanding universe. Beyond this cosmic horizon lie regions of space whose light hasn't had time to reach us since the Big Bang. We can never observe these regions directly, no matter how advanced our technology becomes. The total universe might be infinitely larger than what we can see, or it might have a finite but unimaginably vast size. Some theoretical models suggest our observable universe might be just one bubble in a much larger multiverse. These concepts push not just against the limits of our observation, but against the boundaries of human comprehension itself. The future of cosmic cartography. New observatories like the James Webb Space Telescope are extending our vision deeper into space and further back in time. Advanced gravitational wave detectors like LIGO and Virgo are providing entirely new ways to observe cosmic phenomena, detecting ripples in spacetime itself. These technological advances promise to refine our measurements of cosmic distances and the Hubble constant. They may help resolve current tensions in cosmology and perhaps reveal entirely new aspects of the universe we haven't yet imagined. As our instruments improve, we continue to push back the frontiers of the observable universe, mapping structures at ever greater distances measured in megaparsecs. With each new observation, we refine our cosmic map and deepen our understanding of the universe's structure, history, and evolution. The study of these vast distances reminds us that science is an ongoing journey of discovery, with each answer revealing new questions to explore. In a universe where a megaparsec equals over 3 million light-years, distances so vast they defy intuitive understanding, we continue to extend our cosmic reach through observation, measurement, and theory. The incomprehensibly huge becomes, through science, comprehensible. And Hubble's constant, that fundamental measure of cosmic expansion, continues to guide our understanding of a universe in motion. In the next chapter, we'll explore another cosmic mystery that exists at these vast scales, the invisible dark matter that seems to hold galaxies together despite the universe's relentless expansion. Chapter 6. The Cosmic Ballet, How the Universe Expands. The night sky appears static and unchanging to our human eyes. Stars seem fixed in their celestial positions, galaxies appear as mere smudges of light, and the cosmos gives the impression of eternal stillness. Yet beneath this apparent tranquility lies one of the most profound discoveries in scientific history. Our universe is not static. It is dancing. It is expanding. For every megaparsec, galaxies are receding away at an additional 70 kilometers per second, give or take. This simple relationship, encoded in what we now call Hubble's law, reveals a universe in constant motion, stretching outward in all directions like the surface of an inflating balloon. The implications of this discovery have reshaped our understanding of cosmic history, the fate of the universe, and our place within it. The discovery that changed everything. In the 1920s, astronomer Edwin Hubble made an observation that would forever change our view of the cosmos. Using the 100-inch Hooker telescope at Mount Wilson Observatory, he studied the light from distant galaxies and noticed something peculiar. The light from these galaxies was shifted toward the red end of the spectrum. More intriguingly, the farther away a galaxy was, the greater this redshift appeared to be. This was not a random pattern. It was systematic, mathematical, and profound. By 1929, Hubble formulated what we now know as Hubble's law, the observation that galaxies are moving away from us at speeds proportional to their distance. The relationship was strikingly linear. For every megaparsec of distance, galaxies appeared to be receding at an additional velocity of approximately 70 kilometers per second. This discovery was revolutionary because it contradicted the prevailing view of a static, unchanging universe that had dominated scientific and philosophical thought for centuries. Einstein himself had added a cosmological constant to his equations of general relativity to prevent them from predicting an expanding universe, which he thought couldn't be correct. When Hubble's evidence became clear, Einstein called this adjustment his greatest blunder. The universe was indeed expanding, and Hubble had provided the evidence. But what does this expansion actually mean for us, for galaxies, and for the cosmos as a whole? Understanding cosmic distances. To appreciate the significance of Hubble's discovery, we must first understand the vast scales involved. A megaparsec, the unit used in Hubble's law, equals approximately 3.26 million light-years. Light traveling at 300,000 kilometers per second takes over 3 million years to cross this distance. For context, our Milky Way galaxy is roughly 30 kiloparsecs in diameter, or just 0.03 megaparsecs. The nearest large galaxy to us, Andromeda, sits at a distance of about 0.78 megaparsecs. These cosmic distances were not easy to measure in Hubble's time. The development of reliable cosmic distance markers has been one of astronomy's greatest challenges. Hubble relied on Cepheid variable stars, whose intrinsic brightness correlates with their pulsation period, making them excellent standard candles for measuring distances. Today, astronomers use a complex ladder of techniques to measure ever greater distances. From parallax measurements of nearby stars to type Ia supernovae visible across billions of light-years, these methods have allowed us to map the expansion of the universe with increasing precision. Each rung of this cosmic distance ladder builds upon the previous one, creating a framework that extends our vision to the edge of the observable universe. Without these tools, we would be unable to test and refine Hubble's law, leaving us blind to the true nature of cosmic expansion. The redshift revolution. The key evidence for the expanding universe comes from the redshift of light from distant galaxies. This phenomenon is similar to the familiar Doppler effect that causes the pitch of an ambulance siren to drop as it passes by. As a galaxy moves away from us, the wavelengths of light it emits are stretched, shifting toward the red end of the spectrum. The greater the redshift, the faster the galaxy is receding. When astronomers analyze the spectrum of light from a distant galaxy, they look for familiar patterns of absorption or emission lines. These patterns act like cosmic fingerprints, identifying specific elements present in the galaxy. When these patterns appear shifted toward the red end of the spectrum, astronomers can calculate precisely how fast the galaxy is moving away from us. The beauty of Hubble's discovery was that this redshift showed a clear pattern. Galaxies twice as far away were receding twice as fast. Those 3 times as distant were moving away 3 times as quickly. This linear relationship is what we now call Hubble's law, and the proportionality constant is the Hubble constant, approximately 70 kilometers per second per megaparsec. This means that for every additional megaparsec of distance, galaxies are receding an additional 70 kilometers per second faster. The redshift revolution transformed cosmology from a largely philosophical pursuit into a precision science. By measuring redshifts, astronomers could determine not just the current state of the universe, but also reconstruct its history and predict its future. The expanding fabric of space. One of the most common misconceptions about cosmic expansion is that galaxies are racing through space away from some central point, like debris from an explosion. This is not what Hubble's law tells us. Instead, it is space itself that is expanding, carrying galaxies along with it. Think of a loaf of raisin bread rising in the oven. As the dough expands, each raisin moves away from every other raisin. There is no center to this expansion. From the perspective of any raisin, all other raisins appear to be moving away, with more distant raisins receding faster. This is precisely what we observe in the universe. Every galaxy sees all other galaxies moving away from it, with the most distant ones receding the fastest. There is no special central point from which the expansion originates. The expansion is happening everywhere, uniformly throughout space. This understanding resolves another apparent paradox. Some galaxies are receding from us at speeds greater than the speed of light. How can this be, when Einstein's theory of relativity tells us nothing can travel faster than light? The answer lies in understanding that the galaxies themselves are not moving through space faster than light. Rather, the space between us and those galaxies is expanding so rapidly that the total recession velocity exceeds light speed. The galaxies are not breaking any cosmic speed limits because they are essentially standing still in their local regions of space. It is the stretching of space itself that creates the appearance of superluminal recession. The Hubble constant controversy. While the general principle of Hubble's law is well established, determining the exact value of the Hubble constant has proven surprisingly difficult. When Hubble first calculated it in 1929, he arrived at a value of about 500 kilometers per second per megaparsec. This would imply a universe only about 2 billion years old, younger than the Earth itself, which we knew was impossible. Over the decades, as measurement techniques improved, the value was revised downward. By the 1970s, there were essentially two camps. One group, led by Alan Sandage, favored a value around 50 kilometers per second per megaparsec. Another group, led by Gerard de Vaucouleurs, argued for a value closer to 100. The difference had profound implications for the age and evolution of the universe. The launch of the Hubble Space Telescope in 1990 was partly motivated by the need to resolve this dispute. A key project of the telescope was to measure Cepheid variables in distant galaxies to determine a more precise value for the Hubble constant. This effort, led by Wendy Friedman, yielded a value of about 72 kilometers per second per megaparsec. Today, the most precise measurements come from two very different approaches. The Planck satellite, which measured the cosmic microwave background radiation left over from the Big Bang, gives a value of about 67.4 kilometers per second per megaparsec. Meanwhile, measurements of type Ia supernovae and Cepheid variables give a value closer to 73. This discrepancy, while seemingly small, is statistically significant and may point to new physics beyond our current understanding. The resolution of this Hubble tension remains one of the most active areas of research in modern cosmology. Dark energy and the accelerating universe. Perhaps the most surprising discovery about cosmic expansion came in the late 1990s. Two independent teams of astronomers were using type Ia supernovae to measure the expansion rate of the universe at different epochs. They expected to find that the expansion was slowing down over time due to the gravitational attraction of all matter in the universe. Instead, they found the opposite. The expansion of the universe is accelerating. This astonishing discovery, which earned the 2011 Nobel Prize in Physics, implied the existence of some kind of energy permeating all of space and pushing galaxies apart with increasing strength over time. This mysterious force was dubbed dark energy. Dark energy now appears to constitute about 68% of the total energy content of the universe. Its nature remains one of the biggest unsolved problems in physics. Is it a property of space itself, as Einstein's cosmological constant would suggest? Is it a new field or particle that we have yet to detect directly? Or does it signal a fundamental misunderstanding in our theories of gravity? The accelerating expansion has profound implications for the ultimate fate of the universe. Rather than eventually slowing down and perhaps even reversing into a big crunch, the universe now appears destined to expand forever, growing increasingly cold and empty as galaxies move beyond each other's visible horizons. This big freeze or heat death scenario paints a bleak picture of the cosmos in the extremely distant future. The age of the universe. One of the most important applications of Hubble's law is determining the age of the universe. If we know how fast the universe is expanding now, we can work backward to calculate when all matter would have been compressed into a single point, the moment of the Big Bang. With a Hubble constant of approximately 70 kilometers per second per megaparsec, the age of the universe works out to roughly 14 billion years. This age estimate aligns well with other independent measurements, such as the age of the oldest stars and the detailed patterns in the cosmic microwave background radiation. However, the calculation is complicated by the fact that the expansion rate has not remained constant over time. In the early universe, the expansion was slowed by the gravitational attraction of matter. More recently, as dark energy has come to dominate, the expansion has begun to accelerate. Accounting for these changing dynamics gives us the more precise figure of 13.8 billion years that cosmologists currently accept as the age of the universe. This vast timescale provides the canvas on which the entire cosmic story unfolds, from the formation of the first atoms to the emergence of stars, galaxies, planets, and ultimately, life capable of contemplating its own origins. The future of cosmic expansion. As we look to the future, the accelerating expansion driven by dark energy paints a picture of cosmic loneliness. Galaxies beyond our local group will eventually recede so rapidly that their light will never reach us. The observable universe will shrink, not because the universe itself is contracting, but because more and more of it will lie beyond our cosmic horizon. In about 100 billion years, any astronomers in our galaxy would see only a handful of nearby galaxies. All evidence of the vast cosmic web of galaxies, clusters, and superclusters that we observe today would be gone, making it impossible for them to discover the true nature and history of the universe. This sobering thought highlights the privileged moment in cosmic history in which we find ourselves. We live at a time when the evidence of cosmic expansion is still visible to us, allowing us to piece together the remarkable story of our universe's birth, evolution, and ultimate fate. The dance of the expanding cosmos continues all around us, invisible to our eyes but revealed through the patient work of science. From Hubble's first measurements to the precision cosmology of today, we have transformed our understanding of the universe from a static, eternal backdrop to a dynamic, evolving stage on which the drama of existence plays out. For every megaparsec, galaxies are receding away at an additional 70 kilometers per second, give or take. This simple relationship contains within it the entire history and future of our cosmos, a universe not merely existing, but becoming. Chapter 7. Beyond the cosmic horizon where light cannot reach. The universe beyond our sight. The night sky presents us with a paradox. When we gaze upward, we see countless stars and galaxies, yet what we observe is merely a fraction of what exists. Beyond our visual reach lies a vast cosmic expanse where galaxies are receding from us at speeds that challenge our fundamental understanding of physics. As we learned in the previous chapter, for every megaparsec of distance, galaxies move away from us at an additional 70 kilometers per second. This seemingly simple relationship leads to an extraordinary conclusion. If we look far enough into the cosmos, we inevitably reach distances where galaxies are moving away from us faster than the speed of light itself, approximately 300,000 kilometers per second. This realization fundamentally alters our perception of the universe's boundaries and raises profound questions about what lies beyond our cosmic horizon. The speed of light has long been considered the universal speed limit. Einstein's theory of relativity established that no object with mass can accelerate to or beyond this speed. Yet here, we find galaxies apparently breaking this cosmic speed limit, moving away from us at velocities exceeding 300,000 kilometers per second. How can this be possible without violating the laws of physics that have served as the foundation of modern astronomy? The answer lies not in the motion of galaxies through space, but in the expansion of space itself. The galaxies aren't actually moving through space faster than light. Instead, the fabric of spacetime between us and these distant objects is stretching. This distinction is crucial for understanding the true nature of our expanding universe. Imagine a loaf of raisin bread dough rising in the oven. The raisins aren't moving through the dough, but as the dough expands, the distance between raisins increases. If the loaf were large enough, raisins on opposite ends would appear to move away from each other faster than any raisin could physically move through the dough. This analogy, while simplified, captures the essence of cosmic expansion, measuring the immeasurable. To comprehend these vast cosmic distances, astronomers use the megaparsec as a standard unit of measurement. 1 megaparsec equals approximately 3.26 million light-years, or roughly 30 quintillion kilometers. At these scales, our solar system becomes invisibly small, and even our Milky Way galaxy, spanning 100,000 light-years, becomes merely a cosmic speck. The Andromeda Galaxy, our nearest major galactic neighbor, sits at a distance of about 0.78 megaparsecs. At this relatively close cosmic distance, it's actually moving toward us due to local gravitational interactions, defying the overall expansion pattern. But beyond our local group of galaxies, the expansion of the universe dominates. The Virgo cluster, a collection of about 1,500 galaxies, lies approximately 16.5 megaparsecs away and is receding from us at roughly 1,200 kilometers per second. The Coma cluster, at about 100 megaparsecs distant, moves away at around 7,000 kilometers per second. When we observe galaxies billions of light-years away, we're seeing them as they existed billions of years ago, when the universe was much younger. The light from these ancient galaxies has been traveling through expanding space for billions of years to reach our telescopes. During this journey, the wavelengths of light are stretched by the expanding universe, shifting toward the red end of the spectrum, a phenomenon known as cosmological redshift. This redshift provides astronomers with a powerful tool for measuring cosmic distances. The greater the redshift, the more the universe has expanded since the light began its journey, and thus the more distant the source. The most distant galaxies we can observe have redshifts indicating they're more than 13 billion light-years away, seen as they were when the universe was in its infancy. The cosmic horizon, where the universe disappears. At a certain distance, approximately 14.4 billion light-years in proper distance, lies what astronomers call the cosmic horizon. Beyond this boundary, galaxies are receding from us faster than the speed of light due to cosmic expansion. Light from objects beyond this horizon will never reach us, no matter how long we wait. This doesn't mean these distant regions don't exist. The observable universe, everything within our cosmic horizon, is merely a fraction of the entire universe. Current models suggest the total universe could be at least 250 times larger than what we can observe, and possibly infinite. The concept of the cosmic horizon highlights an important distinction between the observable universe and the entire universe. The observable universe includes everything from which light has had time to reach us since the Big Bang, approximately 13.8 billion years ago. The entire universe encompasses all that exists, including regions from which light will never reach us due to cosmic expansion. This raises profound questions about the nature of reality. If parts of the universe are fundamentally unobservable to us, can we truly understand the cosmos in its entirety? Are there phenomena beyond our cosmic horizon that might challenge or even contradict our current understanding of physics? These questions remind us of the limits of human knowledge and the vastness of what remains unknown. The Hubble tension, a cosmic controversy. The relationship between distance and recession velocity is described by the Hubble constant, named after astronomer Edwin Hubble, who first observed this relationship in 1929. The value of this constant tells us how fast the universe is expanding. Determining its precise value has become one of the most pressing issues in modern cosmology. Different measurement techniques have yielded slightly different values for the Hubble constant, creating what scientists call the Hubble tension. Measurements based on the cosmic microwave background, the afterglow of the Big Bang, suggest a value of about 67.4 kilometers per second per megaparsec. However, measurements based on observations of supernovae and other standard candles in the relatively nearby universe suggest a value closer to 73 kilometers per second per megaparsec. This discrepancy might seem small, but in the precision world of cosmology, it's significant enough to suggest either measurement errors or, more intriguingly, new physics. Perhaps the expansion rate has changed over time in ways our current models don't account for. Or perhaps there are fundamental aspects of the universe we haven't yet discovered. This tension between different measurements of the Hubble constant represents one of the most exciting frontiers in cosmology today. The fabric of spacetime. To truly understand cosmic expansion, we must grasp Einstein's revolutionary concept of spacetime. In Einstein's general theory of relativity, space and time are not separate entities, but are woven together into a four-dimensional fabric called spacetime. This fabric can be warped and stretched by the presence of mass and energy. The expansion of the universe is not objects moving through space, but the stretching of spacetime itself. This distinction allows distant galaxies to appear to recede faster than light, without violating Einstein's cosmic speed limit. No object is moving through space faster than light, but the accumulation of expanding space between distant galaxies and us can make their relative recession velocity exceed the speed of light. Imagine drawing two dots on a deflated balloon, then inflating it. The dots move apart not because they're moving across the balloon's surface, but because the surface itself is expanding. If the balloon were large enough, dots on opposite sides would separate faster than anything could travel across the balloon's surface. This analogy helps us visualize how galaxies can appear to recede faster than light without breaking any physical laws. The fabric of spacetime itself is stretching, carrying galaxies along with it like dots on an expanding balloon. Cosmological redshift, light-stretching journey. When light travels through expanding space, its wavelength is stretched, shifting it toward the red end of the spectrum. This cosmological redshift differs from the Doppler effect, which occurs when a source of light moves through space. In cosmological redshift, the light's wavelength increases as space itself expands during the light's journey. The formula Z equals lambda observed lambda emitted. Lambda emitted gives us the redshift value Z, where lambda represents wavelength. A galaxy with Z equals 1 has had its light wavelengths doubled by cosmic expansion, indicating significant distance. The most distant galaxies observed have redshifts exceeding Z equals 11, meaning their light has been stretched by a factor of 12 or more. At these extreme distances, visible light from these galaxies is shifted into the infrared spectrum, requiring specialized telescopes like the James Webb Space Telescope to detect them. These highly redshifted galaxies show us the universe as it was in its infancy, less than 1 billion years after the Big Bang. They provide crucial data for understanding how galaxies formed and evolved in the early universe. The study of these ancient, distant galaxies helps us piece together the cosmic story of how the first stars ignited, how the first galaxies assembled, and how the universe transformed from a hot, dense plasma to the vast cosmos we observe today. The fate of the universe. The current acceleration of cosmic expansion, attributed to the mysterious force called dark energy, has profound implications for the universe's ultimate fate. If dark energy maintains its current properties, the expansion will continue to accelerate indefinitely. In this scenario, known as the Big Freeze or heat death, the universe will grow increasingly sparse and cold. Galaxies beyond our local group will eventually recede beyond our cosmic horizon, disappearing from view. In the far future, trillions of years from now, even nearby galaxies will appear increasingly redshifted and dimmer. Eventually, the observable universe will consist only of our local group of galaxies, with everything else having receded beyond our cosmic horizon. Stars will burn out, black holes will evaporate through Hawking radiation, and the universe will approach a state of maximum entropy, a cold, dark expanse where no new stars form and no work can be done. However, if dark energy's properties change over time, other fates become possible. If dark energy weakens, gravity might eventually halt and reverse the expansion, leading to a big crunch, where all matter collapses back into a singularity. Alternatively, if dark energy strengthens, it could tear apart all structures in the universe from galaxy clusters down to atoms, in a scenario called the Big Rip. The ultimate fate of our universe hinges on the nature of dark energy, which remains one of the greatest mysteries in modern physics. Living in an expanding cosmos. The concept of galaxies receding faster than light challenges our intuitive understanding of the universe. It reminds us that the cosmos often defies common sense, operating according to principles that can seem paradoxical from our limited human perspective. Our cosmic horizon represents a fundamental limit to what we can observe, no matter how advanced our technology becomes. There will always be parts of the universe that remain forever beyond our reach, invisible and unknowable. Yet rather than diminishing our cosmic quest, these limitations make the exploration of the observable universe all the more precious. Every observation of distant galaxies, every measurement of cosmic expansion, adds to our understanding of the magnificent cosmos we inhabit. As we peer deeper into space and further back in time, we continue to refine our cosmic story, a narrative that connects us to the stars and galaxies through shared origins and shared physical laws. The universe's vastness and complexity humble us, yet its comprehensibility through mathematics and physics speaks to the remarkable capacity of the human mind to understand the cosmos of which it is a part. In the next chapter, we will explore another cosmic mystery that shapes our understanding of the universe's structure and evolution: the enigmatic dark matter that binds galaxies together and forms the cosmic web upon which the visible universe is built. Chapter 8. The Cosmic Speed Limit, when light is not fast enough. Imagine staring deep into the night sky with the most powerful telescope ever built, gazing farther and farther into the cosmos. At some point, you would reach a boundary beyond which you could see nothing more. This is not because your telescope lacks power, but because you have reached the edge of the observable universe. This boundary exists not because the universe ends there, but because the light from objects beyond this point will never reach us, even though light is the fastest thing in the cosmos. The speed of light represents the ultimate cosmic speed limit, a fundamental constant woven into the very fabric of our universe. The universe's ultimate speed limit, the speed of light in a vacuum, approximately 299,792,458 meters per second, stands as nature's ultimate speed limit. Nothing with mass can travel faster than this cosmic speed limit, a cornerstone of Einstein's special theory of relativity published in 1905. This isn't merely a technological limitation we might someday overcome, but a fundamental property of spacetime itself. When Einstein formulated his revolutionary theory, he overturned centuries of Newtonian physics by showing that space and time are not separate entities, but are woven together into a single fabric called spacetime. One of the most profound implications of this theory is that the speed of light is constant for all observers, regardless of their relative motion. This seemingly simple statement has extraordinary consequences. As an object with mass accelerates toward the speed of light, its energy requirements increase exponentially. To reach the speed of light itself would require infinite energy, making it physically impossible for any massive object to attain this speed. Consider what happens as an object approaches light speed. Time dilation occurs, meaning time passes more slowly for the fast-moving object compared to a stationary observer. If a spacecraft could somehow accelerate to 99.9% the speed of light, the passengers might experience a journey of just a few years while centuries pass on Earth. Simultaneously, the object would experience length contraction, appearing shortened in the direction of motion, and its mass would appear to increase from an outside observer's perspective. These effects aren't just theoretical, but have been confirmed in particle accelerators, where subatomic particles routinely reach 99.999% the speed of light. The GPS satellites orbiting Earth must account for these relativistic effects to maintain accuracy, as they travel fast enough for time dilation to be measurable, measuring the vast cosmic distances. To comprehend the truly mind-boggling scales of our universe, astronomers have developed specialized units of measurement. While light years capture the imagination by defining distance in terms of how far light travels in a year, nearly 9.5 trillion kilometers, professional astronomers often prefer the parsec. 1 parsec equals about 3.26 light years, and for truly cosmic scales, we use megaparsecs, with each megaparsec representing 1 million parsecs, or about 3.26 million light years. The threshold of 4,300 megaparsecs mentioned in our opening represents a critical boundary in our cosmic understanding. This distance, approximately 14 billion light years, marks a special horizon in our universe. To put this in perspective, our nearest galactic neighbor, the Andromeda Galaxy, sits a mere 0.78 megaparsecs away. The Virgo cluster, the nearest substantial galaxy cluster to us, is about 16.5 megaparsecs distant. The Coma cluster, one of the richest galaxy clusters we can observe, lies about 100 megaparsecs from Earth. Yet these cosmic structures, vast as they seem, are practically in our cosmic backyard compared to the 4,300 megaparsec threshold. Measuring such distances requires ingenious techniques. Astronomers use cosmic distance ladders, starting with nearby objects whose distances can be measured directly, then using these as stepping stones to gauge farther objects. Type Ia supernovae serve as standard candles, exploding with predictable brightness that allows astronomers to calculate their distances based on how dim they appear. Cosmic background radiation patterns provide another measurement tool, helping map the universe's large-scale structure. These measurements reveal that our observable universe extends about 46.5 billion light-years in any direction, giving it a diameter of roughly 93 billion light-years. When galaxies outrun light, Here we encounter one of the most counterintuitive aspects of modern cosmology. Galaxies beyond approximately 4,300 megaparsecs are receding from us faster than the speed of light. At first glance, this seems to violate Einstein's cosmic speed limit, but there's a crucial distinction to be made. Special relativity states that nothing can move through space faster than light. However, in an expanding universe, space itself can expand at any rate. Galaxies aren't moving through space faster than light, but the space between galaxies is expanding so rapidly that the total recession speed exceeds light speed. This concept stems from general relativity and the expanding universe model first proposed by Belgian Priest and physicist Georges Lemaître, and later supported by Edwin Hubble's observations. Hubble discovered that galaxies are moving away from us at speeds proportional to their distance, a relationship now known as Hubble's law. The farther a galaxy, the faster it recedes. At the critical distance of about 4,300 megaparsecs, this recession velocity equals the speed of light. Beyond this cosmic horizon, galaxies recede faster than their light can travel toward us. Consequently, the light emitted today by these ultra-distant galaxies will never reach Earth, no matter how long we wait. They have, in a very real sense, disappeared from our observable universe. The light we currently see from these distant objects was emitted billions of years ago when they were closer, and their recession velocities were lower than light speed. As the universe continues expanding, more galaxies will cross this threshold, gradually shrinking our observable universe in terms of what we can interact with in the future. The observable universe versus reality. Our observable universe represents just a fraction of what likely exists. The observable universe includes everything from which light has had time to reach us since the Big Bang, approximately 13.8 billion years ago. Due to cosmic expansion, this creates an observable sphere with a radius of about 46.5 billion light-years, not 13.8 billion as might be expected, because space itself has expanded during light's journey. However, cosmological models strongly suggest the universe extends far beyond this observable bubble. Inflation theory, which explains the universe's remarkable uniformity, indicates that our cosmos underwent an incredibly rapid expansion in its first fraction of a second. This inflationary period would have stretched the universe to dimensions vastly exceeding our observable portion. Some models propose that the actual universe might be at least 250 times larger than what we can observe, while others suggest it could be effectively infinite. If the universe is indeed infinite, then the 4,300 megaparsec threshold represents an infinitesimally small fraction of what exists. Beyond our cosmic horizon lie countless galaxies, stars, and potentially even civilizations that we will never see or contact. These regions are not just temporarily beyond our view, but are permanently inaccessible to us due to the fundamental physics of an expanding universe. Light's losing race against expansion. For light emitted today from galaxies beyond our cosmic horizon, cosmic expansion presents an insurmountable challenge. As this light travels toward us, the space it must cross continually stretches, effectively creating more distance to cover. It's like running on a treadmill that accelerates faster than you can run. No matter how long the light travels, it will never reach us. This cosmic expansion also affects the light that does reach us from distant objects. As light traverses expanding space, its wavelength stretches, a phenomenon known as cosmological redshift. The farther the light source, the greater this redshift. For the most distant observable galaxies, their light has been stretched from ultraviolet and visible wavelengths to infrared and even radio waves by the time it reaches our telescopes. This redshift provides astronomers with a valuable tool for measuring cosmic distances and the expansion rate of the universe. The James Webb Space Telescope, with its infrared capabilities, was specifically designed to observe these highly redshifted distant galaxies, allowing us to peer further back in cosmic time than ever before. As we observe objects near the edge of our observable universe, we're seeing light that has traveled for nearly the entire age of the universe. These ancient photons began their journey when the universe was just a few 100 million years old, long before our solar system or even our galaxy had formed. Time, light, and cosmic history. When we gaze at distant celestial objects, we're looking back in time. The light from the moon takes about 1.3 seconds to reach Earth, meaning we see the moon as it was 1.3 seconds ago. The sun appears as it was about 8 minutes ago. The nearest star beyond our solar system, Proxima Centauri, is seen as it was roughly 4.2 years in the past. This time delay becomes increasingly significant as we observe more distant objects. The Andromeda Galaxy appears as it was 2.5 million years ago, when early humans were just beginning to use stone tools. Galaxies at the edge of our observable universe are seen as they were over 13 billion years ago, shortly after the Big Bang. For galaxies beyond the 4,300 megaparsec threshold, we can only observe their ancient past, when they were still within our observable universe. Their present state and future evolution will remain forever unknown to us. This creates a cosmic timeline that we can never update or complete. We see these ultra-distant galaxies as they were in their infancy, never to witness their maturity or eventual fate. As cosmic expansion continues to accelerate, driven by the mysterious force called dark energy, more galaxies will cross beyond our cosmic horizon. The observable universe will appear to grow emptier over trillions of years, as fewer galaxies remain visible. Eventually, in the far distant future, observers in our galaxy might see only the local group of gravitationally bound galaxies, with everything else having receded beyond the cosmic horizon. The big picture, our cosmic understanding. Modern cosmological models have revolutionized our understanding of the universe's structure and evolution. The Lambda CDM model, which incorporates dark energy and cold dark matter, currently provides the best explanation for the observed large-scale structure and expansion of the universe. This model predicts a universe that began in a hot, dense state about 13.8 billion years ago, and has been expanding ever since. The initial inflationary period, occurring just 10 seconds after the Big Bang, expanded the universe exponentially, smoothing out irregularities and setting the stage for the formation of galaxies and larger structures. After inflation, the universe continued expanding at a slower rate, allowing matter to coalesce under gravity. About 7 billion years ago, the expansion began accelerating due to dark energy, which now constitutes about 68% of the universe's total energy content. This acceleration drives the cosmic horizon phenomenon we've discussed, where galaxies beyond 4,300 megaparsecs recede faster than light. Observations from missions like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and the Planck satellite have provided strong evidence supporting this model. These spacecraft measured minute temperature fluctuations in the cosmic microwave background radiation, the afterglow of the Big Bang, revealing the seeds of cosmic structure and confirming many predictions of inflationary theory. The universe appears to be geometrically flat, meaning parallel lines remain parallel even over cosmic distances, which suggests its total size may be infinite. Philosophical implications of cosmic limits. The existence of a cosmic horizon raises profound philosophical questions about the nature of knowledge and our place in the universe. There are regions of the cosmos that we can never observe or interact with, no matter how advanced our technology becomes. This places fundamental limits on what we can know about the universe as a whole. If the universe extends infinitely beyond our observable bubble, then the portion we can study represents an infinitesimal fraction of reality. This humbling realization echoes the Copernican principle, which states that humans do not occupy a privileged position in the cosmos. Not only are we not at the center of the universe physically, but our very ability to observe and understand the universe is constrained by cosmic horizons. Some philosophers and physicists have proposed that if the universe is infinite, then everything physically possible must occur somewhere, including exact duplicates of Earth and everyone on it. This mind-bending implication arises because an infinite universe with finite possible particle configurations must eventually repeat those configurations. The cosmic speed limit and the resulting horizon also reinforce the isolation of humanity in the cosmos. Even if intelligent life exists in galaxies beyond our cosmic horizon, we can never communicate with or even detect them. Our light signals will never reach them, and theirs will never reach us. This creates distinct causal patches of the universe, forever disconnected from one another. Despite these limitations, the fact that we can understand these cosmic principles at all speaks to the remarkable capabilities of the human mind. Through mathematics and physics, we can comprehend aspects of the universe far beyond our direct experience. The cosmic speed limit may constrain what we can observe, but it doesn't limit our ability to theorize about what lies beyond. As we continue to explore the observable universe with increasingly powerful instruments like the James Webb Space Telescope and future gravitational wave observatories, we push closer to the boundaries of what can be known. Though we may never see beyond our cosmic horizon, our understanding of the universe's vastness and complexity continues to expand, reminding us of both our limitations and our extraordinary capacity for comprehension. In the next chapter, we will explore the mysterious substance that makes up about 27% of our universe, yet remains invisible to our telescopes. Dark matter, the cosmic scaffolding upon which galaxies and the largest structures in the universe are built. Chapter 9. The Edge of Sight, our Cosmic Speed Limit. Introduction. The universe has a speed limit. Not just any speed limit, but one that fundamentally constrains what we can see, know, and understand about our cosmos. When we gaze into the night sky, we might imagine that with a powerful enough telescope, we could see everything that exists. But reality imposes a more humbling truth. There exists a boundary in our universe that no observation can ever penetrate, a cosmic horizon beyond which galaxies recede from us faster than their light can travel toward us. Oh yeah, definitely we even have a name for the point at which galaxies are receding away at the speed of light: the Hubble horizon. This invisible boundary represents not just a limit to our vision, but to our very knowledge of the cosmos. It's a reminder that the universe may be far vaster than what we can ever observe. In this chapter, we'll explore this cosmic speed limit, understanding how the universe's expansion creates a fundamental boundary to observation, and what this means for our place in the cosmos. The cosmic speed limit. When Einstein formulated his special theory of relativity, he established that nothing can travel faster than light. This cosmic speed limit of 299,792,458 meters per second seems absolute. Yet the universe has found a loophole. While no object can move through space faster than light, space itself faces no such restriction. Space can expand at any rate, carrying galaxies along with it like raisins in rising dough. The farther a galaxy is from us, the faster it appears to recede due to this expansion. At a certain distance, roughly 14.4 billion light-years away in our current epoch, galaxies appear to recede at exactly the speed of light. This boundary is what we call the Hubble horizon, named after Edwin Hubble, who first observed that galaxies are moving away from us at speeds proportional to their distance. This horizon represents a fundamental limit to what we can observe. Beyond this boundary, galaxies recede faster than light speed. No signal from these regions, not even light, can ever reach us. They exist beyond our cosmic horizon, forever unobservable. It's important to understand that these galaxies aren't breaking Einstein's speed limit. They aren't moving through space faster than light. Rather, the space between us and them is expanding so rapidly that the total recession rate exceeds light speed. Think of ants on an expanding rubber sheet. The ants might walk slowly, but if the sheet stretches quickly enough, two ants can separate faster than their walking speed would ever allow. The expanding universe. To truly grasp the Hubble horizon, we must first understand cosmic expansion. In the 1920s, Edwin Hubble made a groundbreaking discovery by observing that distant galaxies were moving away from us. More surprisingly, he found that the farther a galaxy was, the faster it seemed to be receding. This relationship, now known as Hubble's law, is described by a simple equation, v equals h0 times d, where v is the recession velocity, d is the distance, and h0 is the Hubble constant. The Hubble constant tells us how fast space is expanding. Current measurements place it at about 70 kilometers per second per megaparsec. This means that, for every megaparsec, about 3.26 million light-years of distance, galaxies appear to recede an additional 70 kilometers per second faster. A galaxy 10 megaparsecs away recedes at 700 kilometers per second. A galaxy 100 megaparsecs away recedes at 7,000 kilometers per second. Eventually, at about 14.4 billion light-years, this recession velocity reaches the speed of light. This expansion isn't like an explosion with galaxies flying outward from a central point. Instead, space itself is stretching everywhere, like a balloon inflating. Every point sees other points moving away, with no special center. From any galaxy in the universe, observers would see the same pattern we do, a cosmic expansion carrying distant objects away from them. Light's race against expanding space. When a photon of light leaves a distant galaxy heading in our direction, it begins a cosmic race. The photon travels at the speed of light through space, but the space it travels through is itself expanding. For photons coming from galaxies within our Hubble horizon, they make progress toward us faster than the space between us expands. Eventually, these photons reach Earth, allowing us to see those galaxies. But for photons emitted by galaxies beyond the Hubble horizon, it's a losing battle. The space between us and the photon expands faster than the photon can traverse it. Like a swimmer fighting against a current that's stronger than their swimming speed, these photons never reach us. In fact, they get farther away from us with time, despite moving toward us at light speed through their local space. This creates a profound limit to our observations. No matter how long we wait or how powerful our telescopes become, we will never see light from galaxies currently beyond our Hubble horizon. They exist in our universe but remain forever invisible to us. It's a humbling reminder of the limits of knowledge imposed by the very nature of our expanding cosmos. The observable universe versus the universe. This brings us to an important distinction: the difference between the observable universe and the universe as a whole. The observable universe consists of everything we can potentially see, everything within our cosmic horizon. It's a sphere centered on Earth with a radius of about 46.5 billion light-years. This radius is much larger than 13.8 billion light-years, the age of the universe, because it accounts for cosmic expansion during the time light has been traveling to us. But the actual universe may extend far beyond this observable bubble. We have no way of knowing how much larger the entire universe might be. Some cosmological models suggest it could be hundreds of times larger than what we can observe. Others propose it might be infinite. The key insight is that our cosmic horizon isn't a boundary in space. It's a boundary in our knowledge. The universe doesn't end at this horizon. Our ability to observe it does. This horizon is also not fixed, but changes over time as the universe's expansion rate changes. During the early universe, when expansion was decelerating, our observable universe was growing. More distant regions were coming into view as their recession velocities dropped below the speed of light. But now, with dark energy accelerating cosmic expansion, the opposite is happening. Galaxies that are currently visible will eventually accelerate beyond our horizon, disappearing from view forever. Cosmological redshift and the horizon. As light travels across expanding space, its wavelength stretches. This phenomenon, known as cosmological redshift, provides a direct measurement of cosmic expansion. The farther light travels through expanding space, the more its wavelength lengthens, shifting toward the red end of the spectrum. For galaxies approaching the Hubble horizon, this redshift becomes extreme. Light from galaxies at the very edge of our observable universe is redshifted by a factor of over 1,000. This means ultraviolet light emitted by those galaxies arrives at Earth as radio waves, stretched by cosmic expansion during its journey. As we look at galaxies closer and closer to the Hubble horizon, their redshift approaches infinity. At the horizon itself, light would be redshifted to infinite wavelength, meaning it would never reach us. This creates practical challenges for astronomers. Detecting highly redshifted light requires specialized instruments sensitive to infrared and radio wavelengths. The James Webb Space Telescope was specifically designed with this challenge in mind, capable of detecting infrared light from the earliest galaxies. But even with our most advanced technology, there remains a fundamental limit to how far back in time and how far out in space we can observe. The evolving horizon. The Hubble horizon isn't static. Its distance changes based on the universe's expansion rate, which has varied throughout cosmic history. In the early universe, during the inflationary period, space expanded at an enormous rate. The Hubble horizon was much closer then, severely limiting what regions could communicate with each other. This had profound implications for the universe's development. Regions that are now visible to each other were once beyond each other's horizons, unable to exchange information or reach thermal equilibrium. After inflation ended, the universe's expansion slowed, and the Hubble horizon expanded faster than the universe. This allowed previously isolated regions to come into causal contact. For billions of years, our observable universe grew as more distant regions came into view. But about 5 billion years ago, dark energy began to dominate the universe's energy content. This mysterious force accelerates cosmic expansion, causing the Hubble horizon to once again grow more slowly than the universe expands. As a result, galaxies are now freezing into place in our cosmic view. In the far future, galaxies outside our local group will accelerate beyond our horizon. Eventually, observers in the distant future will see only their local galaxy group, with all other galaxies having receded beyond their Hubble horizon. Misconceptions about cosmic speed limits. The concept of galaxies receding faster than light often creates confusion. Doesn't this violate Einstein's cosmic speed limit? The key distinction lies in understanding what special relativity actually forbids. Einstein's theory prohibits objects from moving through space faster than light. It places no restrictions on how quickly space itself can expand. Galaxies beyond our Hubble horizon aren't moving through space faster than light. They're essentially stationary in their local space, just as we are in ours. It's the intervening space that expands, carrying these galaxies away from us at apparent superluminal speeds. Another common misconception involves confusing the Hubble horizon with the particle horizon. The particle horizon marks the maximum distance from which light could have reached us since the beginning of the universe. It defines our observable universe. The Hubble horizon, in contrast, marks where galaxies currently recede at light speed. These two horizons coincide only in certain cosmological models, but in our dark, energy-dominated universe, they differ significantly. Finally, many assume that the Hubble horizon represents some kind of physical boundary in space. It doesn't. It's purely an observational limit, a consequence of cosmic expansion and the finite speed of light. Space continues beyond this horizon, populated with galaxies we'll never see. A conclusion. The Hubble horizon represents one of the most profound limits in science, a boundary not to our universe but to our knowledge of it. It reminds us that the cosmos may be far vaster than what we can observe, with potentially infinite realms forever hidden from our view. This cosmic speed limit shapes our understanding of the universe's structure and evolution. It influences how we interpret the cosmic microwave background, how we model the distribution of galaxies, and how we conceptualize our place in the cosmos. Perhaps most importantly, the Hubble horizon teaches us humility. No matter how powerful our instruments become or how clever our theories grow, there will always be parts of the universe beyond our ability to observe. We are confined to our cosmic information bubble, with the light speed barrier and cosmic expansion working together to limit what we can know. Yet within these constraints, we've managed to piece together a remarkable understanding of cosmic history, from the Big Bang to the formation of galaxies to the acceleration of the universe's expansion. In the next chapter, we'll explore another mysterious component of our universe, one that makes up about 27% of its content, yet remains invisible to our telescopes. Dark matter, the cosmic scaffolding upon which galaxies and the largest structures in the universe are built. Chapter 10. Beyond the light barrier, cosmic speed and expanding horizons. It's inevitable that distant galaxies beyond a certain point recede, away faster than light speed. Yet this statement often causes confusion. How can anything move faster than light when Einstein told us this is impossible? The answer lies in a crucial distinction that reveals one of the most profound insights about our universe. The cosmic speed paradox. When Einstein formulated his special theory of relativity, he established that nothing can accelerate through space faster than light. This cosmic speed limit of 299,792 kilometers per second remains unbroken within spacetime itself. No spacecraft, particle, or signal can exceed this fundamental barrier. But Einstein's equations say nothing about the expansion of space itself. The fabric of the universe operates under different rules than the objects within it. Imagine two ants on the surface of a balloon. As the balloon inflates, the ants might walk toward each other at a constant speed, yet still find the distance between them increasing if the balloon expands rapidly enough. The ants haven't violated any speed limits in their movement across the balloon's surface, but the expansion of their domain creates an effect that seems to defy their locomotive capabilities. In our universe, galaxies aren't racing away from us through space. Rather, the space between galaxies stretches, carrying them along like raisins in an expanding loaf of bread. This cosmic expansion occurs everywhere simultaneously, with no central point. From our perspective on Earth, this creates the illusion that we occupy a special position, as all distant galaxies appear to recede from us. But observers in those galaxies would see exactly the same phenomenon from their vantage point. The rate at which galaxies appear to move away increases with distance, a relationship first observed by Edwin Hubble in the 1920s. This pattern, now known as Hubble's law, reveals that for each megaparsec of distance, galaxies recede about 70 kilometers per second faster. This value, the Hubble constant, represents the current expansion rate of our universe. The implications are staggering. At approximately 14.4 billion light-years from Earth lies what astronomers call the Hubble horizon. Galaxies beyond this boundary recede faster than light speed. Yet this doesn't violate relativity because these galaxies aren't moving through space faster than light. Rather, the expansion of space itself carries them away at apparent superluminal velocities. Cosmic horizons and boundaries. This expansion creates fundamental limits to what we can observe. The observable universe isn't the entire universe, but merely the portion we can detect. Light from regions beyond our cosmic horizon hasn't had time to reach us since the Big Bang, roughly 13.8 billion years ago. This boundary, called the particle horizon, defines the spherical region from which light has had sufficient time to reach an observer since the beginning of cosmic time. But there's another boundary with profound implications for our cosmic future, the event horizon. Unlike the particle horizon, which shows us the past limit of what we can observe, the event horizon represents a future limit. Light emitted today from galaxies beyond our cosmic event horizon will never reach us, no matter how long we wait. The accelerating expansion of the universe ensures these signals will forever outrun our ability to detect them. This creates a sobering reality. The observable universe is shrinking in terms of what we can potentially interact with. Galaxies currently visible will, over cosmic time, accelerate beyond our event horizon, disappearing from view forever. Future astronomers billions of years hence will observe a dramatically emptier sky, with fewer and fewer galaxies visible as cosmic expansion isolates our local group of galaxies from the rest of the universe. This phenomenon creates what cosmologists sometimes call cosmic loneliness, as galaxies become increasingly isolated in an ever-expanding void. Misconceptions about cosmic speed limits. Popular understanding of relativity often misses these nuances. Einstein never claimed nothing could move faster than light under any circumstances. He specified that nothing can accelerate through spacetime beyond this limit. The distinction proves crucial for cosmology. Another common misconception involves the idea that galaxies at the edge of the observable universe recede at exactly the speed of light. In reality, due to the changing expansion rate throughout cosmic history, galaxies currently visible to us may recede faster than light. We can see them because their light was emitted when they were moving more slowly, allowing their signals to begin journeys that eventually reached Earth. The expansion of space itself has no speed limit. During the inflationary period immediately after the Big Bang, space expanded at an exponential rate, far exceeding light speed. This period of hyperinflation lasted just a fraction of a second, but expanded the universe by a factor of at least 10^26, an almost incomprehensible growth rate. This rapid expansion explains why regions of the universe that could never have been in causal contact, nevertheless, share remarkably similar properties, solving the horizon problem that once puzzled cosmologists. Measuring cosmic recession velocities. How do astronomers determine how quickly distant galaxies move away from us? The primary tool is redshift measurement. As light travels through expanding space, its wavelength stretches, shifting toward the red end of the spectrum. The greater the redshift, the faster the recession velocity. Edwin Hubble's groundbreaking work established the relationship between distance and redshift, providing the first evidence for an expanding universe. Modern techniques have refined these measurements with extraordinary precision. The Hubble Space Telescope's key project determined the Hubble constant to about 10% accuracy. More recently, the Planck satellite measured cosmic microwave background radiation to constrain this value even further. Astronomers also use Type Ia supernovae as standard candles to measure cosmic distances with remarkable precision. These stellar explosions have consistent intrinsic brightness, allowing scientists to determine their distance by measuring their apparent brightness from Earth. By combining distance measurements with redshift data, astronomers calculate recession velocities for galaxies billions of light-years away. The most distant galaxies observable today have redshifts exceeding 11, meaning their light has been stretched by a factor of 12 since emission. These objects recede at velocities approaching 3 times the speed of light, yet we can still see them because their light began its journey when they were much closer to us. The accelerating universe mystery. Perhaps the most surprising discovery in modern cosmology came in 1998, when 2 independent teams of astronomers found that cosmic expansion isn't slowing down as expected, but accelerating. This revelation, which earned the 2011 Nobel Prize in Physics, fundamentally changed our understanding of cosmic destiny. The acceleration implies the existence of a mysterious repulsive force that overcomes gravity on the largest scales. Cosmologists call this force dark energy, though its true nature remains one of the greatest unsolved mysteries in physics. Dark energy appears to behave like a property of space itself. As the universe expands, creating more space, the total amount of dark energy increases, accelerating expansion ever faster. This runaway process ensures that galaxies beyond our local group will eventually accelerate beyond our ability to observe them. Various theoretical models attempt to explain dark energy's nature. Einstein's cosmological constant represents one possibility, describing dark energy as vacuum energy inherent to space itself. Quintessence models propose a dynamic field that varies across time and space. Modified gravity theories suggest our understanding of gravitational forces requires revision at cosmic scales. The accelerating expansion changes our cosmic fate dramatically. Rather than eventually recollapsing in a big crunch or expanding at an ever-slowing rate, our universe appears destined for a big freeze or heat death scenario. In this future, galaxies beyond our local group will disappear from view as expansion carries them beyond our cosmic horizon. Stars will exhaust their fuel and die, leaving an increasingly cold, dark, and diffuse cosmos. Implications for cosmic destiny. The concept of superluminal recession velocities reshapes our understanding of cosmic destiny. The observable universe represents just a fraction of what exists. Regions beyond our cosmic horizon remain forever inaccessible, creating fundamental limits to knowledge. As expansion accelerates, the observable universe effectively shrinks. Galaxies currently visible will eventually disappear beyond our cosmic horizon, their light unable to overcome the expanding gulf between us. In the far future, perhaps 1 trillion years hence, astronomers would observe only our local group of galaxies. All evidence of the broader cosmic expansion would vanish from view. This raises profound questions about knowledge and scientific understanding. Future civilizations might develop entirely different cosmological models based on their limited observations, unable to detect the true expanding nature of the universe. The cosmic horizons created by expansion establish absolute limits to what we can potentially know about our universe. No technology, regardless of advancement, can overcome these fundamental barriers imposed by physics itself. Yet within these constraints, humanity has managed to piece together an astonishing cosmic narrative, deducing the universe's age, composition, and evolution despite our limited vantage point. This achievement stands as testament to the power of scientific inquiry and human ingenuity. The universe beyond the light barrier reminds us of both the limits and possibilities of knowledge. While we cannot observe everything that exists, we can understand the rules governing what we see, allowing us to infer what lies beyond our cosmic horizon. As we peer outward at galaxies receding faster than light, we glimpse not just distant objects but the fundamental nature of spacetime itself. The cosmic speed limit paradox reveals how the universe operates according to elegant physical principles that allow for both structure and expansion, creating a cosmos both comprehensible and mysterious. In this vast, expanding universe, we find ourselves in a unique position to witness cosmic evolution during a specific era, when many galaxies remain visible before accelerating beyond our view. This perspective grants us insights that may be unavailable to astronomers in the distant future, when evidence of cosmic expansion will have receded beyond detection. The universe beyond the light barrier continues to challenge our understanding, reminding us that even our most fundamental physical principles contain subtleties and exceptions that reveal deeper truths about reality. As we explore these cosmic horizons, we expand not just our knowledge of the universe but our appreciation for its magnificent complexity. Chapter 11. The Precision of Understanding. In the universe wrong, what? Well, you've brought up great points because they force us to be more precise in what we say. Einstein showed us that precision in language is not merely an academic exercise, but the very foundation of scientific breakthrough. When we casually say something is wrong in the universe, we often mean it contradicts our intuition or our simplified models. But the universe itself cannot be wrong. It simply is. Our descriptions of it, however, can be incomplete, imprecise, or fundamentally flawed. This chapter explores how the quest for precision has driven our deepest insights into cosmic reality, and how casual imprecision continues to create confusion in our understanding of the universe. The language of precision. Einstein once remarked, "If you can't explain it simply, you don't understand it well enough." Yet this quote itself requires precision in interpretation. Simplicity in explanation doesn't mean oversimplification of complex phenomena. Rather, it means distilling concepts to their essential elements without losing their fundamental accuracy. The revolution Einstein brought to physics wasn't just mathematical, it was linguistic. Before Einstein, physicists spoke of absolute time and absolute space as if these were unquestionable realities. The language itself constrained their thinking. Einstein's breakthrough came partly from questioning these very terms. What exactly do we mean by simultaneous? What precisely constitutes a reference frame? By demanding precise definitions for these seemingly obvious concepts, Einstein revealed that our casual understanding was fundamentally imprecise. Consider how we commonly speak about gravity. We say objects attract each other, as if some mysterious force reaches across empty space. Einstein's precision forced us to reconsider this language. In general relativity, objects don't attract each other through empty space. They follow the straightest possible paths through curved spacetime. This linguistic shift wasn't merely semantic. It represented a fundamental reconceptualization of reality. The precision of language revealed the precision of nature itself. When we discuss quantum mechanics, linguistic precision becomes even more crucial. Terms like wave function collapse or quantum uncertainty are often casually misused in ways that create genuine misconceptions. Even professional physicists sometimes fall into the trap of speaking as if quantum particles have definite positions and momenta simultaneously, despite Heisenberg's uncertainty principle explicitly forbidding this. The language we use shapes the questions we can ask, and the questions we ask determine the answers we can find. Common misconceptions through imprecise language. Perhaps nowhere is the need for precision more evident than in discussions of the expanding universe. When we say the universe is expanding, casual listeners often picture galaxies flying outward into pre-existing space, like debris from an explosion. This mental image, created by imprecise language, is fundamentally wrong. The expansion of the universe refers to the stretching of space itself. Galaxies aren't moving through space like bullets. The space between them is growing. Similarly, when discussing black holes, casual language often creates misconceptions. We speak of black holes as sucking in matter, as if they were cosmic vacuum cleaners. This imprecise language creates an incorrect mental model. Black holes don't actively pull matter in any more than the Earth actively pulls a falling apple. Matter follows the extreme curvature of spacetime near a black hole, a passive geometric effect rather than an active force. Even the term black hole itself can be misleading. A black hole is neither black in the conventional sense, nor is it a hole in space. It is a region where spacetime curvature has become so extreme that the escape velocity exceeds the speed of light. The casual language we use to describe these phenomena often trades accuracy for accessibility, creating persistent misconceptions that can be difficult to correct. When we discuss the Big Bang, imprecision leads many to imagine an explosion at a particular location in pre-existing space. The more precise description involves the entire observable universe beginning as an extremely hot, dense state, with space itself expanding from that initial condition. There was no outside for it to expand into. There was no before in any conventional sense of time. The imprecision of everyday language simply fails to capture these counterintuitive realities. Einstein's legacy of precision. Einstein's approach to physics demonstrated the power of precise thinking. His famous thought experiments weren't merely clever illustrations. They were exercises in precision that revealed the logical consequences of physical principles. Consider his famous elevator thought experiment. By precisely defining what an observer would experience in an accelerating elevator versus one in a gravitational field, Einstein revealed the equivalence principle that would become the foundation of general relativity. The precision of his thinking allowed him to see connections that others had missed. Einstein's insistence on operational definitions revolutionized physics. He didn't merely ask what time is in some abstract sense. He asked specifically how we measure time, what procedures we follow, what instruments we use. This operational approach cut through centuries of philosophical confusion about the nature of time and space. By focusing on precisely what we can measure, rather than abstract concepts, Einstein grounded physics in observable reality. His precision extended to mathematics as well. When existing mathematical tools proved inadequate for describing curved spacetime, Einstein embraced tensor calculus. This mathematical precision allowed him to express general relativity in equations that have withstood a century of experimental tests. The precision of Einstein's approach continues to influence physics today. Modern theoretical physics demands mathematical rigor and conceptual clarity that would have been unimaginable before Einstein. Even when theories venture into realms that seem speculative, like string theory or loop quantum gravity, They maintain Einstein's insistence on mathematical precision and logical consistency. The challenge of explaining the universe, communicating complex scientific ideas, presents a fundamental tension. Complete precision often requires mathematical formalism inaccessible to most people. Yet simplification risks creating misconceptions that can be difficult to correct. Richard Feynman captured this dilemma perfectly. If I could explain it to the average person, it wouldn't have been worth the Nobel Prize. Yet Feynman himself was a master of finding the balance between accessibility and accuracy. His famous diagrams simplified quantum electrodynamics without sacrificing its essential features. This tension between precision and accessibility has only grown more acute in the century since Einstein. Quantum mechanics and general relativity defy simple analogies. The multiverse hypothesis and string theory push against the limits of what can be expressed in everyday language. Yet scientists must try to communicate these ideas to colleagues, students, and the public. The challenge is finding language that is precise enough to avoid misconception, yet accessible enough to be understood. Popular science writers often use metaphors and analogies. Space is described as a fabric that can be warped by mass. Quantum particles are likened to waves and particles simultaneously. These analogies can be powerful tools for building intuition, but they must be used with care. Every analogy breaks down at some point, and without clarity about where those breakdowns occur, misconceptions flourish. The most successful science communicators acknowledge the limitations of everyday language while using it to build bridges to more precise understanding. They recognize that precision isn't just about being technically correct. It's about creating accurate mental models that can guide intuition without misleading it. Confronting misconceptions in physics. Some of the most persistent misconceptions in physics stem from imprecise language and oversimplified explanations. Let's examine a few of these misconceptions and how greater precision can resolve them. Many people believe that objects in orbit are weightless because they've escaped Earth's gravity. This imprecise understanding leads to confusion. In reality, the International Space Station experiences about 90% of the gravitational pull it would feel at Earth's surface. The apparent weightlessness comes from continuous free fall, not the absence of gravity. Precision in explanation resolves this misconception. Another common misconception involves the nature of scientific theories. In everyday language, we often use theory to mean guess or speculation. This imprecision leads many to dismiss well-established scientific theories as merely tentative hypotheses. In science, a theory is a comprehensive explanation supported by vast evidence and capable of making testable predictions. The theory of evolution and the theory of general relativity aren't guesses. They're robust frameworks confirmed by mountains of evidence. Even the term law in physics creates misconceptions. Many believe scientific laws are absolute rules that can never be broken. More precisely, scientific laws are concise mathematical descriptions of observed patterns, valid within specific contexts. Newton's laws of motion aren't wrong. They're approximations that work extremely well at everyday speeds but break down at velocities approaching the speed of light. This more precise understanding helps resolve the apparent contradiction between Newtonian mechanics and relativity. Perhaps the most fundamental misconception involves the scientific method itself. The simplified version taught in schools suggests a linear progression from hypothesis to experiment to conclusion. The reality is far more nuanced, involving feedback loops, peer review, replication, and theoretical frameworks. Greater precision in describing how science actually works helps combat misunderstandings about scientific consensus and the nature of scientific knowledge. The dialogue between theory and observation. Scientific progress emerges from the continuous dialogue between theoretical precision and observational evidence. Theories make precise predictions. Observations test those predictions. Discrepancies drive refinement of theories or occasionally spark scientific revolutions. Einstein's general relativity predicted that light would bend around massive objects like the sun. The precision of this prediction allowed Arthur Eddington to design the famous 1919 eclipse expedition specifically to test it. When observations confirmed Einstein's predictions, it wasn't just a triumph for relativity. It was a triumph for the dialogue between precise theory and careful observation. This dialogue continues today at the frontiers of physics. The Standard Model of particle physics made precise predictions about the properties of the Higgs boson decades before technology allowed us to test those predictions. When the Large Hadron Collider finally detected the Higgs in 2012, its properties matched the theoretical predictions with remarkable accuracy. Yet this dialogue also reveals the limits of our current understanding. Dark matter and dark energy were postulated precisely because observations of galactic rotation and cosmic expansion didn't match the predictions of our best theories. These discrepancies drive theoretical innovation and observational ingenuity. The precision of our measurements reveals the imprecision of our theories, pushing science forward. Sometimes, apparent discrepancies arise from imprecise experimental techniques or data analysis. In 2011, physicists at CERN reported neutrinos traveling faster than light, contradicting special relativity. Further investigation revealed a loose fiber optic cable had created timing errors in their measurements. This incident highlighted how precision in both theory and experiment is necessary for scientific progress. The most exciting frontiers in physics today lie where theoretical precision and observational evidence seem to conflict. The apparent incompatibility between quantum mechanics and general relativity drives research into quantum gravity. The mysterious acceleration of cosmic expansion challenges our understanding of fundamental forces. These tensions, revealed through precise measurement and calculation, point toward new physics waiting to be discovered. The value of critical questioning. When you point out potential flaws in our explanations of the universe, you're participating in a tradition as old as science itself. Critical questioning drives precision. It forces scientists to clarify their claims, examine their assumptions, and refine their theories. The history of physics is filled with examples where critical questions led to breakthroughs. Max Planck questioned why the spectrum of blackbody radiation didn't match classical predictions, leading to quantum theory. Einstein questioned the absoluteness of time, leading to special relativity. Even the most established theories benefit from critical examination. General relativity has passed every experimental test for over a century, yet physicists continue to devise new tests to probe its limits. This isn't because they expect Einstein to be wrong. It's because precision demands we understand exactly where and how our theories apply. The questions you've raised force us to be more precise in what we say about the universe. This precision isn't merely academic. It's essential for scientific progress. When we speak casually about complex phenomena, we risk creating misconceptions that hinder understanding. When we speak with precision, we create clarity that enables discovery. The greatest scientists have always been the most persistent questioners. Richard Feynman famously said, "I would rather have questions that can't be answered than answers that can't be questioned." This attitude exemplifies the scientific commitment to precision through critical inquiry. Science advances not just through new discoveries, but through more precise formulations of what we already know. Einstein didn't overthrow Newton. He provided a more precise framework that revealed the limits of Newtonian mechanics while encompassing its successes. Your questions about what might be wrong in our understanding of the universe participate in this tradition of refinement through critical inquiry. From Einstein to modern physics, evolving precision. The standards for precision in physics have evolved dramatically since Einstein's time. Modern experiments can detect gravitational waves that stretch and compress spacetime by less than the width of a proton. Atomic clocks can measure time with accuracy of 1 second in billions of years. This increasing observational precision demands corresponding theoretical precision. Quantum field theory can calculate some quantities to 12 decimal places, matching experimental measurements with extraordinary accuracy. The successful prediction of the magnetic moment of the electron is often cited as the most precisely verified theory in the history of science. Yet alongside this increasing precision, we've also discovered fundamental limits to what can be known. Heisenberg's uncertainty principle places precise limits on how accurately we can simultaneously measure certain pairs of properties. Gödel's incompleteness theorems reveal limitations in formal mathematical systems. These discoveries don't undermine precision. They define it more rigorously. Modern physics embraces these limitations, incorporating them into increasingly sophisticated theoretical frameworks. The precision of modern physics extends beyond individual theories to their interconnections. The Standard Model unifies 3 of the 4 fundamental forces in a mathematically consistent framework. Ongoing efforts to incorporate gravity into this picture drive research into string theory, loop quantum gravity, and other approaches to quantum gravity. This quest for unification represents the ultimate expression of theoretical precision. Einstein's dream of a unified field theory continues to inspire physicists seeking a precise, comprehensive description of physical reality. As our understanding evolves, so too does our appreciation for the precision of nature itself. The fundamental constants of physics appear finely tuned to permit the existence of complex structures like galaxies, stars, and life. Whether this apparent fine-tuning reflects a multiverse, a deeper theory, or some other explanation remains an open question. But the precision itself is undeniable. The universe operates according to principles of extraordinary mathematical precision. Our theories strive to match this natural precision, and your questions push us to be ever more exact in our descriptions. In this ongoing quest for understanding, precision isn't just a scientific virtue. It's our best tool for glimpsing the true nature of reality. Chapter 12. The Cosmic Speed Limit. Introduction. In 1905, a 26-year-old patent clerk named Albert Einstein published a paper that would forever change our understanding of the universe. Working in relative obscurity in Bern, Switzerland, this young physicist challenged centuries of established thinking about the fundamental nature of space and time. Einstein's special theory of relativity showed through elegant mathematics and thought experiments that nothing in a vacuum can travel faster than light. This cosmic speed limit, approximately 299,790,2458 meters per second, represents an absolute boundary in our universe, a law of nature as fundamental as gravity itself. To understand why this speed limit exists and what it means for our universe requires us to rethink our intuitive notions of reality. The implications of Einstein's discovery extend far beyond academic physics, influencing everything from the GPS systems in our phones to our understanding of how stars shine and how time itself flows. This chapter explores the revolutionary theory that established the speed of light as the universe's ultimate speed limit, forever changing our relationship with space, time, and energy. The revolutionary insight. Before Einstein, physicists operated under Newtonian mechanics, which suggested that space and time were absolute, unchanging backdrops against which the drama of the universe played out. Isaac Newton had envisioned a universe where time ticked forward at the same rate for everyone, everywhere, and where distances remained constant regardless of how you measured them. This framework had served science well for centuries, accurately predicting everything from the motion of planets to the behavior of objects on Earth. But by the late 19th century, cracks began to appear in this tidy picture of reality. Experiments attempting to detect Earth's motion through the theorized ether that supposedly carried light waves consistently failed. Most notably, the Michelson-Morley experiment of 1887 showed that light always traveled at the same speed regardless of the Earth's motion through space, a finding that defied common sense. Einstein's genius was to take this experimental result not as a problem to be solved, but as a fundamental truth about nature. If light always travels at the same speed for all observers, regardless of their relative motion, then something else had to give. That something was our conception of space and time themselves. Einstein proposed that space and time were not separate, absolute entities, but rather aspects of a single, malleable fabric called spacetime. This realization led to the stunning conclusion that nothing could exceed the speed of light in a vacuum. Unlike other speed limits we encounter, this one isn't merely practical but theoretical. It isn't that we haven't built engines powerful enough, or that we need better technology. The speed of light represents a fundamental barrier woven into the very structure of reality. Time dilation. When clocks disagree, one of the most counterintuitive consequences of Einstein's theory is that time itself is not absolute but relative. Consider two identical twins, one who remains on Earth and another who boards a spacecraft traveling at 99% the speed of light to a distant star and back. When the traveling twin returns, she would be measurably younger than her Earthbound sibling. This isn't science fiction or a theoretical curiosity. It's a measurable effect called time dilation, and it has been confirmed countless times in laboratory settings. Atomic clocks placed on fast-moving airplanes return slightly behind their stationary counterparts. Particles called muons, which should decay before reaching Earth's surface from the upper atmosphere, survive the journey because, from their perspective at near-light speeds, the distance is contracted. Time literally runs slower for objects in motion relative to an observer. The closer an object approaches the speed of light, the more dramatic this slowing becomes. At the speed of light itself, time would stop completely from our perspective. This helps explain why nothing can exceed this cosmic speed limit. As an object with mass accelerates toward the speed of light, time for that object slows dramatically relative to stationary observers. From our perspective, the object would need infinite time to reach light speed, making it physically impossible to break this barrier. Length contraction, the shrinking universe. Just as time stretches for fast-moving objects, space contracts. An object moving at high speed relative to an observer appears shorter in the direction of motion. A meter stick moving at 87%, the speed of light would appear to be only half a meter long to a stationary observer. This phenomenon, called length contraction, further reinforces the cosmic speed limit. As an object approaches the speed of light, its length in the direction of travel would approach zero from the perspective of a stationary observer. Combined with time dilation, these effects create a natural barrier that prevents massive objects from reaching light speed. The universe itself seems designed to enforce this speed limit through the very structure of spacetime. These effects aren't noticeable in our everyday lives because the speeds we typically encounter are so much slower than light speed. Even the fastest human-made objects, like the Parker Solar Probe traveling at about 430,000 miles per hour, move at less than 0.1% the speed of light. At such speeds, relativistic effects are minimal but measurable with precise instruments. E=mc2, the most famous equation, perhaps the most famous outcome of Einstein's special theory of relativity, is the equation E=mc2. This elegant formula expresses the equivalence of mass and energy, showing that they are different forms of the same thing. The equation tells us that even a tiny amount of mass contains an enormous amount of energy, with the conversion factor being the speed of light squared. This relationship explains why nothing with mass can reach the speed of light. As an object with mass accelerates, it gains energy and therefore effective mass. The faster it goes, the more energy is needed to accelerate it further. To reach the speed of light would require infinite energy, an impossibility in our finite universe. The mass-energy equivalence doesn't just explain the cosmic speed limit. It underlies the power of nuclear reactions, both in weapons and in the hearts of stars. The sun shines because it converts tiny amounts of mass into vast amounts of energy through nuclear fusion, following Einstein's equation. Every second, the sun converts about 4 million tons of matter into pure energy, powering all life on Earth. This principle also explains why particles like photons, which have no rest mass, can travel at light speed. With no mass to convert to energy, they are free to move at the maximum possible velocity in our universe. Causality, the arrow of time, the light speed barrier, protects something even more fundamental than our intuitions about space and time. It preserves causality, the principle that causes must precede their effects. If information could travel faster than light, it would be possible in some reference frames for effects to precede their causes, creating paradoxes that violate our understanding of reality. Imagine sending a faster-than-light message to someone 10 light-years away. From certain reference frames, that message would appear to arrive before it was sent, violating the basic principle that effects cannot precede their causes. The speed of light limit ensures that the fabric of cause and effect remains intact throughout the universe. This preservation of causality is perhaps the deepest reason why the cosmic speed limit exists. It maintains the coherence of events across the universe, preventing the kind of paradoxes that would make reality itself incoherent. Experimental confirmation. Einstein's predictions have been tested and confirmed with increasing precision over the past century. From the bending of starlight around the sun during a solar eclipse to the precise timing needed for GPS satellites to function correctly, special relativity has passed every experimental test with flying colors. Modern particle accelerators routinely accelerate subatomic particles to 99.999% the speed of light, and their behavior exactly matches Einstein's predictions. No matter how much energy is added, these particles approach but never reach the speed of light. Even in the most extreme environments in the universe, such as around black holes or in the aftermath of supernova explosions, no violation of this cosmic speed limit has ever been observed. The evidence is overwhelming that Einstein was right. The speed of light in a vacuum represents an absolute cosmic speed limit. Apparent exceptions, quantum entanglement. Some phenomena might seem to violate the cosmic speed limit at first glance. Quantum entanglement, for instance, creates correlations between particles that appear instantaneous across any distance. When measurements are made on entangled particles separated by vast distances, The results show correlations that seem to require faster-than-light communication. However, deeper analysis reveals that no actual information is being transmitted faster than light. The correlations exist, but they cannot be used to send a message or signal faster than light speed. This subtle distinction preserves both quantum mechanics and special relativity, showing how these seemingly contradictory theories can coexist. Similarly, the expansion of the universe itself can carry galaxies away from each other at apparent speeds greater than light. But this doesn't violate relativity because it's space itself that's expanding, not objects moving through space. The cosmic speed limit applies to motion through space, not to the expansion of space itself. Living in a light-speed limited universe, the cosmic speed limit shapes our place in the universe in profound ways. It means that our view of distant galaxies is always historical, showing them not as they are now, but as they were when their light began its journey to Earth millions or billions of years ago. It creates a fundamental horizon beyond which we cannot see, because light from more distant regions hasn't had time to reach us since the beginning of the universe. This speed limit also creates practical challenges for space exploration and communication. Radio signals to Mars can take anywhere from 4 to 24 minutes to make the one-way journey, depending on the planet's relative positions. A conversation with potential future astronauts on Mars would involve frustrating delays between questions and answers. Voyages to even the nearest stars would take decades or centuries with any technology currently conceivable, making interstellar travel a daunting challenge for our species. Yet the same principle that limits our reach across the cosmos powers the stars that make life possible. The cosmic speed limit is not just a frustrating barrier, but a fundamental aspect of a universe that allows for our existence. Einstein's special theory of relativity, by showing that nothing in a vacuum can travel faster than light, didn't just solve a physics problem. It revealed a profound truth about the nature of reality itself. The cosmic speed limit isn't merely a law we've discovered. It's woven into the very fabric of spacetime, a cornerstone of the universe we inhabit. As we look toward the future of space exploration and physics, we do so with the humbling knowledge that some boundaries in nature cannot be broken, only understood more deeply. The light speed limit stands as both a challenge to our ambitions and a window into the elegant mathematical structure that underlies all of physical reality. Chapter 13. The Local Universe, Limitations of Special Relativity. The universe is a grand cosmic theater, where the laws of physics play out across scales, both unfathomably large and impossibly small. While we've explored how special relativity establishes the cosmic speed limit of light, there's an important qualification we must now address. Special relativity, elegant as it is, only applies locally. This simple statement carries profound implications for our understanding of the cosmos. The local nature of special relativity. Einstein's special relativity revolutionized our understanding of space and time. But it comes with an important caveat that is often overlooked in popular discussions. The theory applies specifically to objects moving through space in what physicists call inertial reference frames, meaning frames that are not accelerating. More importantly, it applies locally, within regions of spacetime small enough that the effects of gravity can be neglected. This locality constraint is not a weakness, but rather a defined boundary of the theory's applicability. When Einstein published his special theory of relativity in 1905, he was well aware of its limitations. The equations work beautifully for objects moving at constant velocities relative to one another in flat spacetime. They predict time dilation, length contraction, and the equivalence of mass and energy, all of which have been confirmed experimentally countless times. Yet Einstein himself knew that something was missing. Special relativity doesn't account for gravity, which becomes problematic when we consider the universe at larger scales. To understand why this locality constraint matters, consider a thought experiment. Imagine two spaceships traveling at nearly the speed of light in opposite directions from Earth. According to special relativity, observers on each spaceship would measure the other ship as moving at a speed less than the speed of light, due to the relativistic addition of velocities. This calculation works perfectly within the local environment of our solar system. However, now imagine two galaxies at opposite ends of the observable universe. Due to the expansion of space itself, these galaxies can appear to recede from each other at speeds greater than light. This doesn't violate special relativity because the galaxies aren't moving through space faster than light, but rather the space between them is expanding. Special relativity doesn't address this phenomenon because it doesn't account for the curvature and expansion of spacetime itself. The local nature of special relativity means that it applies within patches of spacetime small enough that we can treat them as essentially flat. Within these local regions, light still moves at exactly 299,792,458 meters per second, and nothing can accelerate past this cosmic speed limit. Beyond special relativity, introduction to general relativity. Einstein spent a decade wrestling with the limitations of special relativity before unveiling his masterpiece, the general theory of relativity, in 1915, where special relativity addresses motion in flat spacetime. General relativity tackles the more complex reality of curved spacetime and the nature of gravity itself. Einstein's journey to general relativity began with what he later called his happiest thought. While sitting in his office at the patent office in Bern, he realized that a person in free fall would not feel their own weight. This equivalence between acceleration and gravity became the foundation of general relativity. The implications were revolutionary. Gravity isn't a force acting across space as Newton had described, but rather the result of massive objects curving the fabric of spacetime itself. General relativity expanded our understanding beyond the local constraints of special relativity. It allowed us to describe the universe at cosmic scales, explaining phenomena that special relativity simply couldn't address. From the precession of Mercury's orbit to the bending of starlight around the Sun during a solar eclipse, general relativity made predictions that have been confirmed with increasing precision over the past century. Perhaps most dramatically, it predicted the existence of black holes, regions where spacetime is so severely curved that not even light can escape. The 2019 image of the shadow of the supermassive black hole at the center of galaxy M87, captured by the Event Horizon Telescope, stands as a testament to Einstein's vision. General relativity also provided the mathematical framework for understanding the expanding universe. When Einstein first applied his equations to the cosmos as a whole, they suggested that the universe couldn't be static, but must be either expanding or contracting. Initially, Einstein introduced a cosmological constant to force his equations to predict a static universe, which was the prevailing view at the time. When Edwin Hubble later discovered that galaxies were indeed moving away from each other, Einstein called the cosmological constant his greatest blunder. Ironically, modern observations suggest that a form of the cosmological constant may
We
indeed
inhabit a little
exist,
blue planet
driving
called
the
Earth.
accelerated
Earth is
expansion of the
habitable
universe
because it had the
through what
right
we now
conditions
call
and
dark
ingredients
energy.
to enable
Inertial
life as we
reference
know it
frames
to
versus
evolve and
accelerating
flourish.
reference
And one of the
frames.
most important
To understand
factors
why
in
special
making our blue
relativity
planet
applies
habitable
only
is the
locally,
wet stuff
we must
itself,
grasp the
water.
distinction between
It's kind of
inertial and
extremely
accelerating
important
reference
for life.
frames.
When
An
it
inertial
comes to the
reference
search for
frame
habitable
is one that is
exoplanets,
not
planets
accelerating,
outside our
moving
solar
at a
system,
constant
we think
velocity
the
through
ability to have
space.
liquid water on a
Special
planet's surface
relativity
is
works
just as
perfectly
important for
within these
those worlds.
frames,
There's
and
a
when
handy
comparing
concept
observations
astronomers
between
use to
different
help them
inertial
figure out where
frames,
to look
the
around
famous
any
twin
given star
paradox
for
illustrates
exoplanets
this
that just
concept.
might have the
One
right
twin
stuff for
stays
life.
on Earth while
It's
the other
called the
travels at
habitable
near
zone.
light speed to
It's
a
the
distant
distance
star
from a
and back.
star where a rocky
When they
planet with an
reunite,
atmosphere
the
could have
traveling
liquid
twin has
water
aged
on its
less due to
surface.
time
In
dilation.
our solar
This
system,
scenario
the habitable
involves
zone extends
acceleration,
from around the
as the
orbit
traveling
of
twin
Venus
must
to
change
around the
direction
orbit
to
of
return
Mars.
home.
Earth happens
Special
to be nice
relativity
and comfy
alone
in the middle,
cannot
but
fully
it takes
resolve
more
this
than just a
paradox.
good location.
We need general
Orbiting in the
relativity
habitable
to
zone
account for
does
the
not
accelerating
guarantee a
reference
planet
frame.
will be
In
habitable.
everyday life,
After all,
we
the
rarely
moon
experience
is right
truly
here with
inertial
us,
reference
but
frames.
it's certainly not habitable.
Earth's rotation
Sorry,
and
moon.
its orbit
The
around the sun
location of the
mean
habitable
we're
zone
constantly
depends on how big
accelerating,
and bright a star
albeit
is.
slightly.
The nearest
The
star to our
gravitational
sun,
pull of
Proxima
Earth
Centauri,
means we
has at
experience a
least one
form of
planet in the
acceleration,
habitable zone.
even when
But
standing
because
still.
Proxima is much
These
smaller
accelerations
and
are
dimmer than
small
our sun,
enough that
its
special
habitable zone
relativity
is way
provides an
smaller
excellent
and closer to the
approximation
star.
for most practical
So
purposes.
every star
However,
has a
in
habitable
contexts
zone,
where
but that doesn't
acceleration
mean
or
there will be
gravity
planets
becomes
there.
significant,
For example, the
general
star known as
relativity
Kepler
becomes
90 is
necessary.
similar to our sun,
Consider a
and
person
it too
in an
has 8
elevator.
planets.
If
but
the elevator
they're all huddled
accelerates
super
upward,
close to
the
the star,
person
well
feels
inside
heavier.
of the habitable
If it
zone.
accelerates
But the
downward,
longer
they
we
feel
look,
lighter.
the more likely
If
it
the
becomes
elevator
that one
cable
day
breaks
we'll
and it
find
falls
another
freely,
little blue,
they feel
water-covered
weightless.
planet right in its
Einstein
own
realized
comfy
that this
habitable zone,
experience
and
of
that
weightlessness
would be
in
a
free
planet
fall
with a
is
closer look
indistinguishable
indeed.
from floating in empty space far from any gravitational source. This equivalence principle became a cornerstone of general relativity. It tells us that acceleration and gravity are two sides of the same coin. The mathematics of general relativity is considerably more complex than special relativity, requiring tensor calculus to describe how matter and energy curve spacetime, and how this curvature in turn dictates the motion of objects. Spacetime curvature and gravity. The concept of curved spacetime represents one of the most profound shifts in our understanding of the universe. In Newton's view, gravity was a force acting instantaneously across empty space. Einstein reimagined gravity not as a force at all, but as the effect of mass on the geometry of spacetime itself. The popular analogy of a heavy ball placed on a stretched rubber sheet helps visualize this concept. The ball creates a depression, and smaller balls rolled nearby will follow curved paths around it, similar to how planets orbit the sun. While this two-dimensional analogy has limitations, it captures the essential idea that mass tells spacetime how to curve, and curved spacetime tells mass how to move. This curvature explains why special relativity applies only locally. In sufficiently small regions of spacetime, the curvature is negligible, and we can treat the region as essentially flat. This is analogous to how a small patch of Earth's surface can be treated as flat for local navigation, even though the Earth is globally curved. The more massive an object, the more it curves the spacetime around it. The Sun creates a significant warp in the fabric of spacetime, causing Earth and other planets to orbit along geodesics, the equivalent of straight lines in curved space. Near a black hole, this curvature becomes so extreme that spacetime folds back on itself, creating an event horizon beyond which nothing can escape. General relativity predicts that massive accelerating objects create ripples in spacetime called gravitational waves. These waves travel at the speed of light and carry energy away from their sources. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, made the first direct detection of gravitational waves, produced by the merger of two black holes 1.3 billion light-years away. This groundbreaking observation not only confirmed another prediction of general relativity, but also opened a new window for observing the universe. Relativistic effects at different scales. The effects of relativity manifest differently depending on the scale we're examining, from the quantum realm to the cosmic web of galaxies and superclusters. At human scales, relativistic effects are typically too small to notice in everyday life. A person running experiences time dilation, but the effect is so minuscule that it would take billions of years of running to gain even one extra second of life compared to someone standing still. Yet modern technology has made relativistic effects relevant to our daily lives in ways we might not realize. The Global Positioning System, GPS, relies on precise timing from atomic clocks aboard satellites orbiting Earth. These satellites move at about 14,000 kilometers per hour relative to observers on Earth's surface, causing their clocks to tick slightly slower due to special relativistic time dilation. Additionally, they experience less gravitational time dilation than clocks on Earth's surface because they're farther from Earth's mass. Without accounting for both these relativistic effects, GPS coordinates would drift by about 10 kilometers per day, rendering the system useless for navigation. At the scale of particle physics, relativistic effects become dominant. Particle accelerators like the Large Hadron Collider routinely accelerate protons to 99.9999991% the speed of light. At these speeds, the proton's mass increases by a factor of more than 7,000 due to relativistic mass dilation. The additional energy manifests as increased mass, following Einstein's famous equation E equals mc2. At cosmic scales, general relativity governs the evolution of the universe itself. The expansion of space, the formation of galaxies, and the behavior of black holes all require general relativity to explain. Even light is bent by the curvature of spacetime, creating phenomena like gravitational lensing, where massive objects like galaxy clusters act as cosmic magnifying glasses, bending and focusing light from distant sources. The precision of language in relativity. When discussing relativity, precision of language becomes crucial. Common phrases like "nothing can travel faster than light" require qualification. More accurately, no object with mass can be accelerated to or beyond the speed of light within a local inertial reference frame. The expansion of space itself is not bound by this constraint. Similarly, statements about time dilation or length contraction must specify the reference frames being compared. Time doesn't simply slow down in an absolute sense. Rather, observers in different reference frames will disagree about the rate at which clocks tick and the length of measuring rods. The famous twin paradox illustrates how imprecise language can lead to apparent contradictions. If motion is relative, why doesn't each twin see the other as aging more slowly? The resolution lies in recognizing that the traveling twin's reference frame is not inertial throughout the journey, as they must accelerate to turn around and return. This acceleration breaks the symmetry between the twins' experiences. Einstein himself was meticulous in his use of language and mathematics. He understood that the concepts of relativity challenge our intuition, which is built from experiences at low speeds and in weak gravitational fields. Clear, precise communication becomes essential when discussing phenomena that lie outside our everyday experience. Experimental verification of relativity theories. The power of relativity theories lies not just in their mathematical elegance, but in their verified predictions. Special relativity has been confirmed through countless experiments, from the increased lifetimes of fast-moving, unstable particles to the precise measurements of relativistic mass increase in particle accelerators. The famous Michelson-Morley experiment in 1887, which failed to detect the motion of Earth through the hypothesized luminiferous ether, set the stage for Einstein's revolutionary ideas. Later, the Kennedy-Thorndike experiment and the Ives-Stilwell experiment provided direct confirmations of time dilation and the relativistic Doppler effect. General relativity has faced equally rigorous testing. The theory's first triumph came in 1919, when Arthur Eddington observed the bending of starlight around the Sun during a solar eclipse, confirming Einstein's prediction. The precession of Mercury's orbit, which Newtonian gravity couldn't fully explain, matched general relativity's predictions precisely. In recent decades, testing general relativity has become increasingly sophisticated. The Gravity Probe B satellite, launched in 2004, confirmed two subtle predictions. The geodetic effect, where a massive body like Earth warps the fabric of spacetime, and frame dragging, where a rotating mass drags spacetime around with it like honey around a spinning spoon.